Okay, good morning to you all. So we are going to start. This is the 5th edition of the In the Black. And this year we will talk about a new era of ocean exploration. And we wish to learn from the past to live the future, to live the present and prepare the future. And I'm going to start by presenting Ricardo, responsible for the Nash Brussels Hub, which is our
only connected to the other TV here presently when people coming from outside. If not, our sound is enough instead of the room. Okay. Paulo, could you please?
So, Ricardo, you're our host. You can present yourself, please.
Yes, hello. My name is Ricardo. Guys, I'll be very fast. Basically, what we do here is we have the Nash Brussels Hub. We have the Nash Brussels Hub here in central Brussels, in the Quartier Européen, as they call it here in the Brussels bubble. I'm not going to take long. I'm just going to show you that the biggest institute of our INESC universe is INESC Tech. It represents a huge percentage of our activity, but we also have INESC Coimbra and 3 INESCs in Lisbon, and we're the largest research and innovation organization in Portugal since 1980. Together with universities and polytechnics, we have a strong world presence, and we are continuing to grow it with new collaborations. And even though we have started as a mainly engineering computer science entity, we now apply those skills and that capacity to many areas. Deep sea mining and all the areas related with the unit that and with the team that is being presented here. But also, if we merge all the capacity, we have these 8 areas that are represented there, from computer science to bioengineering and cybersecurity. We are more than 2,000 people, and in the whole INESC universe. So please don't hesitate to contact us if you want a strong entity with a strong track record to collaborate in European projects and other initiatives. So that's all. Thanks for your attention. I will pass the message, I think, to Eduardo.
Thank you. Good morning for all people present in the room and also people in the net. First of all, I am very happy to be here after 5 years to organize in BLACK. BLACK is a small meeting we start to organize in 2016, I suppose, or 17, I don't remember very well, but I suppose 16 or 17. And we decided to organize because we need to talk about the in black problems and behind the curtain, because we start to thinking on develop some technology for deep sea a lot of years ago. And also we start to work in the deep sea, address the problem of deep sea mining. Maybe 11 or 12 years ago, we developed a proposal. We failed. We developed a proposal, name is Puntos, with leadership from BMT, and this time from UK, and we have this proposal until in the race and until the end, but we lose for the MIDAS. You know, MIDAS is a very important project for impact assessment, and the more technological team. This is a call with 2 phases, and in the end, only 2 proposals arrived to the end, MIDAS and Puntos, but we lose for MIDAS. But the consortium don't broken and don't exist, and we try to continue to contribute for understanding and develop some technology for deep sea. In this time, we know very well Andrew Wheeler from Cork. This is a good geologist from Cork. They have a good experiences in Middle Atlantic Ridge. We work with Patrick Collins in this time is a consultancy for Nautilus, for the impact assessment work in Papua. And we build a good team, but we lose. But in simultaneous you decide, okay, and they have a lot of problems to talk with. Deep sea in the ocean is a forbidden word in these times because the people don't is a problem. Develop technology for underwater, for deep sea, because if you develop technology, the mining appear soon. And we decide, okay, go to start to develop our technology in land. Underwater, you have a lot of mines in land and in the tunnels or in the open pit, and you decide, okay, don't start in the ocean because you don't have money in the next 5 years because the people don't go give you money for that. And they have also a strong consortium based in the Netherlands. Chris started to work with these consortiums, I remember, with the blue mining and this consortium is very strong, very technological also, and we don't have any chance to have money. And we decide to go to work in land, and we apply with Vamos and win, and we start to develop. Our team starts to develop technology, but in the Vamos is technology for exploitation, okay? And yes, after 1 or 2 years, in simultaneous we apply for a project is Mineral Frontiers. We lose. I don't remember if you start to participate in this project.
In Vamos, we started.
No, before Vamos.
No.
Mineral Frontiers. After we lose, after that you have Extremine. We lose, and we win on Extremine. Okay, for exploration, not for exploitation. This is exploration in land. And we start to develop. Now, the results of the next mean is José going to present, as supposed to you, is the robot for the exploration in the flooded land and tunnel mines. And we develop technology in Vamos. And after Vamos, in the middle of the Vamos, we applied to, we see we need more technology for sensing, and we apply in the 80 raw materials and we develop the Insight. This is a spin-off project coming from Vamos in terms of the leaps, underwater leaps, and the next step is the upscaling of UNEXMIN. And we continue to develop technology for underwater, but still in land because of that project to go to the sea. In meanwhile, in home, in Portugal, we apply for projects for develop technologies, and you have the Turtle series. We start to develop technology for structure the seabed, and we still continue to work in several projects. We try several times in Europe to develop more technology. We apply to develop a project to bring the lab to the deep sea. Spectis, we apply with Spectis project. We lose again. The people don't think it's important to bring the lab to the deep sea and kick us from the call and don't give us a good classification. After that, we try to develop technology for exploitation, and again in the sea is the sea Azores with a very, very strong consortium. We lose again. We don't have any chance to have money for that. And also for the side of the corporation, you have another submission. The name is A3 Gyms, and we lose again. And we fail until have again a successful project. In meanwhile, we have some small projects in Portugal or Europe, but our pathway is always to try to have chance to develop technology for that. Fortunately, this new phase of the European project Horizon, we have in the first year we applied to with one call. Unfortunately, it's not yet signed, but I suppose it's going to sign in next week. But in meanwhile, we develop technology based coming from the output of the Vamos. It's very important for us because scientists and researchers and engineers learn to work in dirty and risky space, and also the developments inside of the next mean and after the next step give us some skills and a lot of capacities to to develop for underwater and deep. And you have more chance to develop technology, infrastructure in Portugal. And now we are happy to have chance again. For the next 5 years, we are mixed with a very good multidisciplinary team inside of the Trident. And also, and in Black appear in the parallel side, and we want these meetings very, very informal. We need to discuss face to face. It's not real a classical workshop or a classic conference today, but it's only for people to share our experience. We can share ours, and people. I hope the people can also bring to us some different knowledge, and in the end we can discuss with free minds and without any constraints. And this is, we work from scientists and researchers and also from industry. Today, this panel is diversified. We have people from ISA, International Seabed Authority, Ulrich and Noemi. We have people from industry, Chris, okay, and we have people, researchers like us, SUB, and from CRISO, with a vision from the other Pacific vision. We are Atlantic center, but you come to us with the other vision of that. It's important to us to bring different perspectives, because the solution is fortunately for us, is not in our mind, is in all minds of all people, and we try to bring together today. Is only a small seed for this discussion. If you go to the story of the In Black, we start with biology in the first year. We understand it by the people from biology. We invite a lot of people from biology and geology for the first In Black. And after that, we start to converge to the technology. And today we go to talk about technology. But In Black, we are engineers, but we start our first meetings in Black with people from outside of our knowledge, because we need to understand really the words and really the semantics of the words coming from biology. This is a place, or this is a topic with a lot of the passion. The people discuss with a lot of the passion. Is very emotional because the people, and because really this is a very sensitive topic, and we need to understand this is a very sensitive topic. In our mind, we have a solution for that, but our mind is not. We need the contribution of all people, and today we hope this is more one step in our knowledge, and one more step in our networking to bring to this table more light, and maybe in 3 or 4 years the name of this meeting changing. Is not in black, is in white, or in transparency. In blue. And I hope to change Anna. You need to, next year is black and blue. It's not in black. You need to start to bring the light and to the surface. And I take a lot of time. I return to you in the end. It's better if you start and listen to people with concrete ideas. It's only abstraction discussions. In my opinion, you can interrupt if you want to stop and discuss in a different way. Don't be formal, be informal, and bring to us your ideas for the black. Thank you very much. Paula, can you continue with meeting, please?
Okay, so there was a slight change in the program since Patrick Nadal is sick and couldn't attend. And so we'll pass to José Miguel Almeida, and I will present him. But first, I just want to say that Eduardo, he didn't present himself. So he's the coordinator of Tech4C, which is a strategy of INESC for blue economy. And he was the former coordinator of the Center for Robotics and Autonomous Systems. He's a professor at the School of Engineering at Porto. and he has a PhD in electrical and computer engineering and has more than 80 publications in the in field robotics.
People know. LinkedIn or Google.
Okay, so let's continue. Anna, can you present?
Yeah, after this great presentation, Paula, our host from INESC Brussels Hub, Professor Eduardo, let's move forward to our first part of the session, opportunities for ocean exploration and underwater technologies. So it's my great pleasure to present my boss. So this is a huge responsibility. José Miguel Almeida is the coordinator at INESC Tech's Center for Robotics and Autonomous Systems. He is a professor at the School of Engineering of Porto. And his main research areas are navigation, sensing, perception, and awareness for field robotics application. He had participated in many European and national research projects, coordinating the INESC Tech team in several of them. I would like to highlight VAMOS and UNEX-MIN European projects, and UNEXUP, which was supported by EIT Raw Materials. He was involved in the design of several innovative autonomous robots that you will see, and he's the author of several scientific publications. José Miguel Almeida, the floor is yours to talk about the next frontier for underwater technologies and mining in the deep sea.
Thank you, Anna. Well, let me try to share this. Well, I will present some of what Eduardo already summarized. So I will present what we have been done. First, our installations and some infrastructures, our projects related to sea, only a few of them, and then mining applications and some of the new challenges that we have. So INESC Tech is part of the INESC that Ricardo presents. So we have around 800 researchers, 13 centers. We are one of them. Our main objective is to create robots that are more autonomous and able to address more complex and unstructured and dynamic environments. And we'll see some of these, of the results of this. We have a open space with some pool tests that is essential to validate our systems in the lab. We have hyperbaric chambers to test for pressures. We now have a new one for 750 bars to address even a bit more, and some production facilities. Okay, these are pressure chambers. Let's skip this. Now we design and create these research vessels. So it is a small, low operation cost research vessel. The idea is to have a more easier access with much lower cost than the previous options that we have. It allows 9 researchers to be 3 days in sea with some capabilities to deploy not big equipment, but 1.5 tons and 2 by 2 by 2 meters can deploy. Some research infrastructures that we create, the Tech4C is a national research infrastructure that INESC push it. That research boat is part of this, but we also have an additional lab in the Porto Harbor, and some additional assets to infrastructure, some buoys, some landers to infrastructure, a zone in sea, and allows to have permanent data from that zone. We also in the national research infrastructures, we participate in the EMSO-PT, and you develop EMSO, a node of the EMSO-PT system that is different from the previous one. So we have a mobile node that is a EMSO system mounted in a robotic lander that we'll see after. We have also more two infrastructures, but we'll present later. So what are the driving challenge and objectives? So the Portugal Sea is big, and we several years ago start to creating technology to address it. And the main challenge is deep, is very extensive. So we need to extend autonomy, safety systems to be in that harsh conditions and so on. So we'll see a lot of the projects that are pushing these objectives, and I will present only briefly a few of them because of time. So one that we finished this year was that we built a hyperbaric system to catch deep sea organisms at pressure, so we can bring to the surface, keeping the pressure, so to preserve and in a way that they don't die because of changes of temperature and pressure. Another relate also to bio is these autonomous biosamplers, or these DNA collection systems that we also develop, and they are bringing to more bigger depths now. Another relating also to sea, to locate and help the collection of lost fish nets. Also, it was interesting because we need to optimize costs and put more autonomous for any fisherman can use it. So it needs to be simple. But going to mine. As Eduardo said, we start from land in the two projects, VAMS and UNEXMIN. UNEXMIN starts in 2016. In 3 years we developed 3 prototypes, validating several scenarios. And at the end, we create a spin-off, the consortium create a spin-off, and with that, we submit a upscaling project that is due next up, that tomorrow we'll have the final conference and demonstration in Nemotrin 33. And the robot from next up also have been testing already more than 10 field tests along several places in Europe, from Ukraine, Czech Republic, Hungary, UK, Portugal, so on. So only to have only to see it's slow. Only to have an idea of the system. That robot is a small sphere, completely actuated in all degrees of freedom. It has 6 cameras, 6 laser projectors, so you can map at high resolution, depending on the visibility, between 3 or 7 meters, and also we have several sonars multi-beam scanning sonars that allows even in a turbidity and non-visibility environment be able to operate. And we test even in fully autonomous missions in Cubania mine some months ago. One of the features is the accurate navigation system. So in some of those missions during 3 hours, we arrive at the same position in an area of 30 centimeters and almost no heading 0.3 or 0.5. So let's skip this. Okay, the VAMS project. The idea was although one of the ideas was to validate some technology in land, but we found out that mining in land without taking the water has a lot of advantage. So we can mine more vertically, so much less energy consumption, we are not drying the area around the mining site. We reduce risks of leakage and problems with the reject dams and others. But since we don't take the water, we need to have a solution for the operators and a system for operators to work. And INESC participate in this project. So in this large consortium, we address the development of support valves, the development of a mine machine, and INESC Tech address mainly the perception, navigation, and awareness of the system. So we use sensors in the mine machine, sensors in the support AUV that we developed for initial mapping of the site, and also work as a third external eye of the mine machine, and integrate that information now we call a digital twin of the mining systems, so that the operator could play like a game, send missions, see how it works. It was because in the beginning the operators are ROV operators, and they want to see the raw data. In the first trial, it was a fight with them for them to use the system. In the second trial, it was the opposite. If we stop for changing or improvement something, hey, what happened? I cannot work like this. So they were fully dependent of the system. It was amazing to see that. But it is hard to change the minds, but yeah, with time and working together. So this is how it looks like. The mining machine was mining sometimes, and it was calm. We were like in a lake. We could be fishing because no noise, no pollution, so it can be supplied with electricity, and it works very nice. Okay, but in that project, I skip it soon. Also, INESC start developing a tool was to use leaves in order to analyze in real time the grade content and validate that, but in surface. So we pump the material and only sample it at surface. And in inside projects, we are is a upscaling project of that technology. Start from that, and we are developing more compact modules, leaves systems to use outside of water, so with additional capabilities, scanning systems, high rates, but also we are putting that to work underwater in order to bring near to the extraction, the characterization, because or else we have a big delay in during rising of the materials to the surface. So, sorry, I'm not sure why the image are degrading a bit, but okay. Let's move on. So this system has been tested last month in the field in Slovenia with some of the people present here. They test in a mine environment and works as we project, and it seems to work very well. Okay, but going to other systems that are in that strategy to address the more permanent systems in sea. These turtle that we start also almost after the Vamos. The idea is to create a lander, but it's not a lander that we deploy, don't know exactly the position, and to retrieve, okay, you can use safe release, but you are leaving things in the bottom, and you need a sport boat to put it again with another heavy weight. So the idea is to have a system that can go to the bottom, land in a precise point, come to the surface when we want, and even charge automatically and go down again without any sport boats. Okay, so we are trying to take all the needs for big assets, big sport boats, and large costs in system. And this was the first prototype. So these have old sensors as AUV, because it is AUV, so it can have precise localization. It can have computers to have missions, so it can be in some points hibernate there or logging at some times, and then move to another position, do that, have large batteries, and he can go changing the buoyancy, so he can change, can become heavy or become light and go to the surface with a low consumption of energy. Now we are in the third version, or this is already ready in test. Now we are in fourth version for 4,000 meters, but these are the actual version working. Several components are already for 4,000 meters. The 4,000 meters is only a bit larger, so we managed to upgrade these for 4,000 meters without scaling too much the weight. It was an engineering fight, but we managed to do that, so it will be around 1 ton, the 4,000 meters. These also have acoustic systems for communication, and we are using these now as in several sport missions applications. So you can use these as a satellites in the bottom to locate, to give the localization for a mining machine or for the AUV doing surveys or other things. You can use these combining a surface buoy, and these can go charge in buoy and go back. So we are extending the permanence of it. So although we as better can have 2 months missions, we are trying to extend this for a more permanent application. In that line also of work for the increasing presence in sea, we have another project that is exploring the underwater cables, fiber optic cables, and use the nodes that do the regeneration of signal to be used as access points to transmit data or receive data and also energy. So the idea is to have some infrastructure in sea to also support some autonomous systems in communications and energy. And we are applying some these in some of the scenarios. So one is seeing how robotic systems can help in the energy. So in NEO's course, we are assessing the possibility to use these assets, so AUVs, landers, ROVs, also above the water on AUVs to do the using these heterogeneous pack of vehicles, address both wind, waves, and all offshore energy solutions. Why these robotics tools? Okay, we think that this can provide the effective, reliably real-time data. So it's not possible to have large quantities of data and in covering large scales with a lot of research vessels because it's too expensive. So this can turn economically viable those missions and the only way to have that information, and that can contribute to a better awareness of all activities, not only mine, but every activities in sea and deep sea can be. We have more information, we can have better decisions to see, okay, this is good, this is bad. How should we work to address this? And one of the applications is the impact assessment of the resource exploration. That is the project that Eduardo also referred, where the concept is to using the concept is more broad, so but that integrates a lot of areas. But the part of robotics is to use a lot of systems communicating to. So we are bringing all the information to offshore to we don't need to have scientists inside with sport boats. We can have all the information going to some cloud or some information center that they can have access to everything. And the idea is to use these robotics to do the monitorization in near field, medium, large, with different type of robots, from gliders for the long ranger to turtles that can be around and supporting the operation of AUVs for more precise data. And the communications, we can create a box that use the communication system of machine to provide communication to the surface, or buoys that also require another logistic process. But we think that it's possible to manage and address these with very low requirements in support systems to do the maintenance of this. So to finish, okay, so to address this, we are increasing the permanence of the robots. We are creating robotic systems to support the other robots. So from providing the positioning, communication, energy. So we need to provide energy to the other assets, but also to do the maintenance, to transport, to recover, to deploy. So we can have robots that deploy other robots. Big main ships that can even go to the deploying place, do all the installation, recovers without having huge costs. and we can also go to having systems to support some operation down there. So if you pass some of the processing systems to avoid other transport problems, and even for underwater cargo transport. And okay, those were briefly the ideas. Sorry if I take too much time.
So let's go to our next speaker, Dr. Ulrich Schwarz-Champera. That's right? Okay. So he's a program management officer for mining geology at the International Seabed Authority in Kingston, Jamaica. He studied geology and paleontology and mineralogy at the universities of Clausthal and Aachen, Germany, and received his PhD on the Trace Metal Association in volcanic hosted massive sulfide deposits and hydrothermal vent fields in the Southwest Pacific from the Freiberg University of Mining and Technology. Okay, so the floor is yours.
Thank you very much for this nice introduction. Sometimes a surprise of my own past. In the beginning, we heard a little bit about failures applying for projects. I never see it as a failure or being unsuccessful, because any proposal is pushing the limits a little bit further, right? So, and sometimes need some time, and winning a project doesn't mean that it's always so successful, right? So the winning parties, they also expose themselves quite a bit, right? So it's still a challenge, and challenging is also working on autopods. Doing exploration is a very long story about failures and misconceptions and so on. And I've got a good friend in Canada. He's a professor at Laurentian University, and he always says it's kind of serendipity. If it would be easy to find autopods, we all would have one, right? So I don't, but in fact, I should have one, right? It's not so easy to find locations, and we were just yesterday confronted with the idea that mining the seabed is just the start. So when you say, well, it's not easy to define a deposit, and people say, yeah, but afterwards, right? So it's this misconception that the entire seabed is an ore deposit. It's not, right? It's still very challenging, also in larger manganese nodule areas, to define a deposit. It's an occurrence, yet exploration defines occurrences, but not ore deposits. It's a challenge to define an ore deposit which makes sure that that the contractors or anyone who's doing mining can define a reasonable amount of nodules within a distinct period of time and assure the production over a distinct amount of time to produce really metals and commodities. That's a big challenge. It's a big challenge on land, and it's even a bigger challenge on the seabed. So that's something perhaps to keep in mind. I like these pictures because just to talk short quickly about our metal production. So we mined 2021 2.8 billion tons of metals, right? And you see this huge block of iron ore. So everyone is talking about cobalt, nickel, copper, right? Batteries and so on. Well, no. I mean, this is a tiny little amount in compared to what we really need, and it's iron for steel, right? That's absolutely dominating. And together with the iron, there comes nickel. Nickel is the other very, very important use, and nickel is not just for batteries. Batteries is a tiny little amount, right? It's about steel production. Interestingly enough, we do have one participant in this metal market, which is one country, which controls more or less 80% of all the metals which are produced and traded. So the question is whether or not it's always a good idea to rely on provider, one producer, right? Also interesting is that in 2019, there were 3.4 billion tons of metals produced. In 2021, we only have 2.8. This also shows something, saying, well, it's the market is narrow, that's for sure, but market also means transportation, which has posed some problems, not just because of COVID, but also because of COVID. So it's not the way that the commodity needs are always growing, right? Because we're living in quickly changing environments and the world is changing quite a bit. So it's important to keep this in mind. Because I was talking about nickel, I don't know whether or not you can see it. Nickel is still an industrial metal, 2.7 million tons every year, or 21 produced. When we go to copper, copper is big, of course, but to cobalt is a trace element. It just hides to the right corner, right? And it's not as important as people may think when you read news and newspapers, right? But still, it's a very, very important commodity, that's for sure. So we all know these pictures. I don't go through numbers, right? But when humanity believes in electronic mobility, then we have to be aware that this requires a lot of additional metals, which poses many, many big questions on the so-called circular economy. It's just not possible at the moment, right? We will need 185 kilograms of metals for every single car. This may change because battery technologies may change, but up to now it's like this. So there's a big need for metal, not just for cars, as I showed. It's basically steel, right? But also for metals. That's important to know. So we are dealing with challenges when it comes to mining. We all agree, and that's a basic understanding for geologists, but not for everyone, especially not in Europe, because in Europe everyone thinks of only mining, because we don't have any mining left in Europe, which is a big mistake anyway. So there was mining going on, and those are the pictures you can collect widely in the internet. It's nickel production in Indonesia. 75% of nickel comes from tropical soils. We can all decide whether or not that's a pretty good idea to mine tropical soils, because we do have tropical rainforests on top. It's a challenge. Let's keep it that simple. We produce manganese, which produces a lot of dust and so on. We all need manganese every day. We don't know, right? And people not aware. And Chile, on the right-hand side, is a major producer, or the biggest producer of copper. They have problems because they produce copper from 2,500 meters, 3,000 meters elevation, high up in the Andes, and they have to make this production larger because of the forecast and demand and the additional forecasted needs. But they have to go to higher elevations, which is putting a problem. So I need to go back now. I can talk. So, anyways, mining on land also has some issues with getting enough understanding and knowledge, right? Because studying mining at universities is not a thing people want to do in these days anymore. So we do have a loss of mining skills. We do have a loss of engineering when it comes to land-based mining. That's why it's great being here and seeing engineers taking care of, right? That's important, and we can definitely do better than mining soils from tropical areas, right? By robotics and so on. So the first challenges with it comes from mining. Mining is always extractive. I'm always saying, well, any extraction of a carrot, or even of an organic carrot from the ground, is extractive, because we extract potassium, phosphorus from fertilizers, selenium, which is also added to fertilizers and so on. So also for our agricultural extraction, we do need fertilizer, we do need mining. It doesn't come from somewhere, it has to be mined somewhere. So there are challenges with mining. We will need mining in the future, despite the fact that people ignore this fact, but it's a fact. Yeah, we do have the challenges with the green energy transition and the forecast of additional needs in resources. We don't know yet, right? Because we don't know exactly the battery which will be used. There are iron phosphate batteries now, which are less productive. They deliver less energy for the car, but perhaps it's good enough. So all of us don't need to be the first when the stopping lights go to green, right? So we may take our time and say, oh, okay, I'm starting slowly, right? Just like with old cars. So for this, we don't need these strong capacity batteries. So we don't know yet, but still, also iron phosphate minerals. Batteries need minerals from mining anyways. So our aim, or basic aim, should be global net zero, right? We all know that we face huge problems in the future, or no, actually in the actual situation, but also even more in the future. So we need to change our behavior. On the other hand side, I mean, you hear these reports just this week in the raw materials week in Brussels saying, well, we cannot move on like this. We cannot produce these cars. We cannot use resources like we do today. Yeah, that's the typical European view. We need to reduce, but we do have another 3 billion, 4 billion people worldwide, and they want to share all the nice tools. They want to be in the internet. They want to have a laptop because it's necessary. They want to be mobile and so on. And I think it shouldn't be us to tell them, no, you can't, because we screw up, not them. So we have to decarbonize the mining industry. Education and industry needs more mining skill gaps and so on. And of course, we all face the issue that we need to secure our resources in the future, whether or not we like it. Yes, yeah, okay. So, because we talk about seabed minerals, I guess all of you may know the 3 defined seabed mineral systems, which are polymetallic manganese nodules with the polymetallic massive sulfides and cobalt-rich ferromanganese crusts. They all occur at very distinct areas on the seabed, nicely identified where they should occur, but not the entire seabed, as I mentioned in the beginning, not the entire seabed holds minerals for us, and that's important to know. Even the so-called CZZ, which is an area between the Clarion and Clipperton fracture zone in the Central Pacific, this area is just perfect for forming good quality manganese nodules, having always more or less the same composition, but still it's not filled up with manganese nodules. You still have to define a deposit, which makes mining possible in the future. Same with polymetallic massive sulfides. They have an occurrence shape of a football stadium. It seems big, right? But you still have to find a football stadium in a vast area of volcanic ridges, right? And the cobalt-rich ferromanganese crusts are a bit easier because they stick out of the ground, basically, but they occur at shallower depth, but still you need to find the right one with the best thickness and so on. So not the entire seabed will be mined. There's one calculation for the manganese nodules saying the entire CZZ, which is about 5 million square kilometers, right? Only 30% could be, or there's a potential for the mining of 30% of this 5 million square kilometers. This would take, if this happens, right, this would take 1,000 years, right? So we talk about huge areas. We know that in the news, people don't describe it in such a way because they play around with sizes and areas and so on. But to be clear, to be correct, it's a lot of area which needs to be defined, studied, explored, and then eventually there might be exploitation, yes or no, if it's worth it. Okay, as we talk about the area, so coming from the International Civil Authority, UNCLOS, the UN Convention on the Law of the Sea, it defines the area, which is the ocean area beyond national jurisdiction. And what you can see here is a nice map first. So we do have a map of the seabed. And the dark gray areas, this is not belonging to the area because this is national jurisdiction. Everything which is lighter gray is the area. The area covers 181 million square kilometers out of the total of 362 million square kilometers of global oceans. And what you can see here, or may not be able to see because it's pretty small, are the occurrences of polymetallic massive sulfides along ridges. They are not rare. You can see occurrences of cobalt-rich ferromanganese crust in the brownish color, also not rare. And you see prime areas for the occurrence of polymetallic manganese nodules, also not rare. But as I said, it's not just because the conditions are right. It means that there are ore deposits to be fertile mines in the future. To keep this in mind. So up to now, there are 31 exploration contracts with the International Civil Authority. The International Civil Authority was formed as a regulatory body for UNCLOS, for the UN Convention on the Law of the Sea. And it provides opportunities for doing exploration. There were 7 pioneer investors. They did a lot of work in the late 70s. So any news saying for the first time we did this, or the second time we did that, that's not true because everything, even mining test mining was done in the 70s already. And there are nice videos around to see what they did actually. So it's the rejuvenation, the way we approach it for second or even third time now. There are 19 exploration contracts for polymetallic manganese nodules. There are 7 contracts for polymetallic massive sulfide along ridges. And there are 5 licenses for cobalt-rich ferromanganese crusts. Yeah, those are running. These exploration licenses are given for 15 years. So contractors have 15 years time. If they are not ready and they have to prove ready to go the next step, for exploitation, they need to prove that they aren't. And then it's a process to extend the exploration license for 5 years. All pioneer investors, they have extended the license for 5 years and just recently for another 5 years. But as I said, it's not a regular process. They need to argue about it, right? And defend why they are not ready. So there are circumstances which helps, like COVID pandemic. It's obvious that you cannot continue with your exploration activities when you can't go out on the ship. Right? So as I said, the area is 181 million square kilometers. It's big, 50% of the world oceans, right? It's a lot. The contractors' areas are 1.5 million square kilometers for all the licenses. So we talk about little areas. It has a world ocean share of 0.66%. Please keep this in mind when you hear these reports, we're mining the seabed. Ooh, well, no, it's a tiny little area, right? Not of a huge area. But still, it's an issue and we need to address. When it comes to the area itself, it covers basically 1.2% of the area. Still, it's little, it's a small area, but still, it's a distinct impact because it's extractive. No doubt about it. We're talking about contractors' activities. I recently put together the numbers of the contractors' investments and expenses over 20 years because the first licenses were given in 2001. Those are the numbers up to 2021, and we see that 1.58 billion US dollars were spent for exploration. It's a tremendous amount of money. You think, and it is, definitely for me it is, when you talk about the expenses for one single license, I once calculated it with an expert coming from land mining, and because he asked me, how much is it? How much is seabed exploration? And I said, well, we spend 8 million a year for sulfide exploration times 15, 120 million. He said, he was just laughing and said, well, that's exactly the amount we spend during one summer doing airborne geophysics, right?
May I ask, is this included oil and gas exploration?
No.
Only metals?
Only for minerals.
For this 1.2% of
It's
the.
only the International Seabed Authority.
So no oil and gas included?
Oil and gas is totally different, yes.
Okay.
It's outside, because this all occurs in national jurisdiction, and it's outside ISA's activities. Right? So for this, you need to consult Exxon and all these companies. So it's still a lot of money, of course, over 20 years, but when compared to land-based exploration, it's not a tremendous amount, I would say, over 20 years. So what are we doing, or what are the contractors doing with the data? We do have, and that's why I'm telling this, we do have a database, and all contractors are required to report all the data they collect. And 50% of this data, which is environmental data, is public, right? Everything which is related to exploration, of course, is confidential until the contractors decide to make it public, because data for investors and so on. But everything which is environment data is free to use, is public. And this amounts just recently to 82 gigabytes. We do have bathymetric data of mapping of 4.2 terabytes, right? Yeah, I'm inviting everyone, because people always claim we don't know enough, we need to do more, right? But you do have this database, and now we have a tracking system who's consulting our deep data database. From where are they coming, and what is the amount they download? And you would be surprised how little the interest in freely available data for the environment is, right? So it's kind of disappointing from my point of view. So please be invited to use everything which is existing. But it forms a picture, and these are my head. So we also provide this data according to the approval by the contractors to international projects, and we established Area 2030, which is a project to supply contractors data on their approval to the UN Seabed 2030 initiative to have a high resolution map of the ocean floor. As I told before, we do have a great map of all oceans. So when you read, we don't know the oceans at all, and we know the backside of the moon better than the ocean, better than seabed. That's wrong, right? We do have on any point of the global oceans, we do have a resolution of about 463 meters, right? And it's even better towards the poles. So along the equator, it's 463 meters. Towards the pole, it's 100-meter resolution. We do have a great map. Please don't be confused by these comments. It's wrong, right? But we can do better, and that's why the contractors provide their data. 13 of all the 22 contractors approved that we can use their bathymetric data and provide this to the Area 2030 program, and then eventually to the UN Seabed 2030 program, which means that the UN aims in providing a high-resolution bathymetric map of all oceans by 2030. Very challenging program, but the ISA and the contractors are contributing. What we also do, because I was mentioning the lack of use of existing data, so we decided that we do it, right? If no one is interested, we are. So we had a great program called ADSR, Africa's Deep Sea Resources, and we invited experts from African countries. That's a work by one nice colleague coming out of Tanzania, John, and did a compilation of all existing oceanographic data. Also, when people talk about environment, it's always biodiversity. But biodiversity is a fraction of the information which is needed for environmental modeling, right? The big thing is oceanography. So we compiled all the oceanographic data. And you see, I mean, in all oceans, there's a vast amount of oceanographic data, but you can't see it in any publications and so on. So people seem not to be interested, which is kind of disappointing, but eventually they will be. Because we talk about technologies here, we also had a project with a colleague from Cameroon. He was compiling all the metallurgical information, because metallurgy is confidential. We cannot disclose it, of course, right? But we got a nice overview on all our contractors' activities when it comes to metallurgy. And all of them, and that's nice to see, all of them aim at a zero waste concept. Zero waste is a big word because we always produce CO2, right? For example, but it's low waste concept. And that's something we need to do because we cannot throw waste to waste dumps anymore because nobody wants to take it anyway. So we need to end up, or the contractors need to end up only with products. And that's what they aim at. Very nice. And a new project was using potential geothermal energy from hydrothermal vent fields along ridges, because we know that every second there are 350 degrees running out of hydrothermal systems, right? So why not using it? Iceland is doing on land, New Zealand is doing out of volcanic systems, and they know how to run geothermal systems in volcanically active areas. So that's a new project we want to figure out. We had Lucy, she's working in Kenya for geothermal energies, and she calculated that the potential of all known hydrothermal vent fields, there are more ones because not everyone is reported yet. It covers half of Africa's entire geothermal production. So that's a big resource we may or may not address in the future. But keep in mind, because we also talk about the need for energy. Okay, ISA has a roadmap on technology. Background, I don't have to go through all this, but the reason why we're sitting here and why ISA likes this project is a modern approach towards robots, towards technology, towards more intelligent uses of technologies and so on. So I would invite you to consult our roadmap for details, or just invite me in and I can give some details. That's right. We've seen this tool on the left-hand side already, which was designed to explore and potentially exploit flooded open pit mines, right? So any activity on the modern seabed is not too far away from what is actually needed in land mines, because any resource company want to use what it already has, right? And mining is always depends on cut-off grades, which means that there's a lot of metals left behind because they were just not economic during the days when the open pit was created. So there are efforts to mine these things. There are sensors developed being able to work in very harsh conditions. So it's a mutual interest of land mining industry and potential seabed mining industry. So the approaches for mining are different. We do have local resources like sulfides and crust. We need different solutions, and one solution was established 20 years ago, mining for diamonds offshore Namibia. They do use trench cutting devices to remove diamonds offshore up to water depth of 150 meters, so it's still shallow. But according to diamond companies like De Beers, they say those diamonds are the best quality because they do have a long way coming from the origin over the Orange River, South Africa, all the way to the beaches of Namibia, right? So quality is great, it's best, value is great, that's why. So they mine these diamonds with great success. I don't want to talk about Britannia 2 because Chris is doing, but I would like to draw your attention on the drawing from the 1978-79 on the upper right-hand side. So when you see the solution of a collector, it wasn't that much different. Of course, technology changed quite a bit, and it's a drawing, but similar systems were developed way in the past. And the left-hand side just quickly does a calculation by a contractor saying, well, if we mine 4 million tons over 15 years, this area covers 5% of the license area for 14 years, right? And this has a required impact on the commodity market, because if you mine less, you're probably not able to place this on the commodity market, because no one wants to buy your metals, right? You need to be large enough. And the last slide, sorry for being too long. ISA is very busy with environmental monitoring, and this is something like bringing oats to Athens, right? Because the Trident project will focus on monitoring. That's a very, very nice project for ISA as well, because ISA as a regulatory body wants to know who's doing what, when, and where, right? Of course, we need to locate any activities, but also we want to know what's happening to the water column, to the environment. So any monitoring is feeding science, is serving knowledge management, and so on. I don't need to read it. You can have it afterwards. So it's a very, very demanded project. We are happy that it's running soon, right? And we're looking forward to the results. And of course, we are ready to supply any more information we can do. Thank you very much.
Thank you.
So we can move on. And now, great presentation, Dr. Ulrich. And now, before our coffee break, it is my honor to present the only woman of the workshop. No, we have another woman. Thank you so much. It's good. We didn't balance it, but it's okay. You are worth for 2 or 3.
1 leads, 3, 4, 5, 6 is very balanced.
Yeah, and we are worth by 2 or 3. But Noemi Wouters, she has an amazing background. She is a force of nature and a source of energy. She's the program coordinator, marine research at the International Seabed Authority, and she looks forward contributing to further implementation of the Marine Scientific Action Plan. Her background is marine sciences, with a master's in marine and lacustrine sciences and a PhD obtained in Portugal. That is why she speaks Portuguese fluently. She has contributed to marine policy making through her appointment at the European Marine Board. In 2018, she has appointed as a CEO of Blue Bridge, which is the Blue Economy Innovation Center of the University of Ghent, and so on and go on. We could stay here speaking about your background, but Noemi, let's hear from you. We are all looking forward to your talk about science as a cornerstone for sustainable exploitation of deep sea minerals.
Yeah, thank you very much. Thank you for the introduction, and I think Ulrich and I were very grateful to be here. So I think this kind of projects actually is a major driver in our daily jobs, you know, that we can learn from and be involved in projects like this. So it's really an honor to be here. I also want to acknowledge before I start the presence of some familiar faces. And I mean, the European Commission is present, and then JPI Oceans as well. So I think it shows that the interest in the project is existing, and I really appreciate it. I joined the International Seabed Authority 2 months ago. And as mentioned in the introduction, I'm responsible, or I have the honor and the pleasure to be responsible for the Marine Scientific Action Plan. So I will pick in on a few concepts that Ulrich already mentioned in his presentation and drive you through it. So I will start with the key message of my presentation. So this is your take home. As ISA, so we're a body, we don't do any, as Ulrich mentioned, we're a regulatory body, we don't do any research by ourselves, yet we catalyze collaborative research at an international level and for the benefit of humankind. So what's a better place to work than a mission, an organization which has a mission like this? I mean, it's research, it's collaborative, and it's for the benefit of humankind. So this is what ISA aims to do, and we try to do it on a daily basis. I will provide you with a bit of the policy context so that you can understand a bit the setting of the Marine Scientific Action Plan, and I refer to UNCLOS that Ulrich already mentioned, so the United Nations Convention for the Law of the Sea. Now, I'm not a lawyer, but I understand this was visionary, and it continues to be visionary. So it was established in the 80s. And it gave, well, this is moving way too fast, but I'm not sure why. So I will show you the presentation. I'm not sure why it's moving. Okay. So it gives ISA some mandates, and of course, an important mandate is linked to the minerals and exploitation of the minerals. Yet it also very explicitly refers to ISA responsibility to promote scientific research, and it goes beyond the research. One of our responsibilities as well is taking the research results forward and distributing, so increasing the deep sea literacy, so to say, of society based on the science we produce. So I go back one slide, I'm sorry. And we also go beyond that in the sense that our marine scientific research goes hand in hand with capacity development. So we reach out, or we try to support developing states in their efforts as well to contribute to science and the technology developments. Now, the UNCLOS and the mandate that ISA has under UNCLOS also is tightly tied into our strategic action plan and the strategic plan that ISA has currently in place. Now, the letters are too small for you to see, but I will read. So strategic direction 2 and 3 refers to the protection of the marine environment and the promotion of marine scientific research. So it's really at the heart of what we do. So the Marine Scientific Action Plan, why was it conceived? Well, it was conceived as a response, as an answer to a call from a United Nations body as well, so UNESCO IOC. They called 2 years ago for the International Decade for Marine Science for Sustainable Development, so the Ocean Decade. Well, in answer to that, ISA then conceived its Marine Scientific Action Plan. I understand that ISA reached out to UNESCO IOC in the conception of the plan, and they continue to contribute to the development of its plan. And as you see, so the action plan is kind of the top of the pyramid. So it's based on UNCLOS. It's based on the strategic action plan and the high-level action plan of ISA, and it has 6 strategic priorities. So the first one is advancing deep sea knowledge, basically enhance the knowledge. The second one is focused on biodiversity. So we have a project which is funded by the European Commission, which is focused on the taxonomic diversity, so species diversity in the deep sea. The third one is linked to the activities of Ulrich. It's about technology innovation and the technology development. The fourth one focuses on environmental impacts because it's a major concern, and we understand it's a major concern, so we contribute the scientific research in that sense as well. The fifth one is linked to deep sea literacy, as I just mentioned before, and then the sixth one is linked to capacity development. Now, each scientific strategic research priority, so we have 6, has outputs and programs that we run under those umbrella activities of today. We recently analyzed how much of the activities that we plan and we're doing are valued, and it amounts to $1.6 million US, where partially it's funded internally. Now, when we say funded internally, it's actually funded by the member states. So member states contribute financially to the International Seabed Authority, and part of that funding is then directed to marine scientific research. Yet we also do attract external money to give light to the programs we have in mind and the initiatives we have in mind. So to give you an idea, in 2023, we aim to establish 5 memory of understanding with other entities. So it's one way in ISA that we formalize, so to say, our collaborations with institutes and governments, so through memories of understanding. We also have a lot of activities going on, so we organize a lot of workshops and conferences, which is part then links back to the deep sea literacy and getting the message out there. So we have one upcoming next week in Korea, which is linked to SKI, the Sustainable Knowledge Initiative, which is funded by the European Commission and contributes to the Strategic Priority 2, which is linked to biodiversity. I won't go into all the activities we have ongoing. There's a list on our website. You can also inscribe yourself on our newsletter, so you will be informed of the activities we have upcoming. As a next item, I would like to draw your attention to regional environmental management plans. And why I do this is because the science, or part of the science we produce, needs to feed the policy. So we at ISA, we try to feed the science policy interface. So the science serves in a sense, or in certain ways, the policy. As you know, our member states are currently negotiating the rules for exploitation. And so they require some scientific tools to be able to make informed decisions. And RAMP is one example of a tool that helps also the protection of the marine environment. So REMS is short for Regional Environmental Management Plan. It's a proactive measurement tool, like I mentioned, and it's decided by the Council. So the member states decide to its adoption, and yet we do have a legal and technical commission, the LDC. That's kind of the scientific and the technological engine of ISA. So it's experts who progress the science and the technology, and they then propose to the Council their findings and recommendations. So this is the CCZ that Uri already mentioned, the Clear Crippler Zone in the Pacific Ocean. And I just wanted to show the picture. On the right-hand side, you see boxes. Now, those boxes are areas of particular environmental interest. So those are regions which were in the past already identified as having high biodiversity or representing particular habitats that need protection. And so they're currently already protected. And if you look at the surfaces, the total surface which is protected within that area amounts to 40%. So I think it's important to know, as you that part of the deep sea area and the area that exploration is ongoing and where eventually exploitation might occur is already protected. A second region where currently we're developing a management, a REMP, a Regional Environmental Management Plan, is in the Mid-Atlantic. That's a process that's ongoing, and it was also funded or supported by the European Commission. That's a second area where currently we're developing such a plan. So I end by reiterating my key message. At ISA, we catalyze marine scientific research. We do it on a collaborative way at an international level, and by doing so, we also have in mind or try to do it for the benefit of humankind. Thank you very much.
Okay, so we have time for questions.
And also the participants online, please be free to unmute yourself and turn on the camera and interact with the speakers, please. Or write in the chat your question if you are shy.
But if the people present here can do question now or in the
No, we have a time for discussion now.
in the end we have 1 hour.
Maybe I can ask you, what is the status of these mining licenses which were given near Papua New Guinea?
New Guinea, okay.
Because it was some given, then getting back. So
this was a national jurisdiction. That's outside ISA's world, right? This is internal issue, or this was an internal issue with Papua Guinea, the government. And there was Nautilus as an investor that did exploration, and they have to find even reserves and resources, 2.3 million tons. And then they were running out of finances. You can follow it up in the internet. So there are arguments against the government of PNG, and the government of PNG had arguments against Nautilus and so on. But it ended with the bankruptcy of Nautilus.
So nothing is happening at the moment.
No. It's dead. There are no activities at the moment. Also because it's too small, right? So no activity.
This was actually the first attempt to mine these nodules, actually.
No,
it's not nodules.
For sulfides.
For sulfides.
For sulfides, yes, right. It was the first attempt to mine sulfides. For nodules, there was testing in the 70s, as I said. Right? So that's not the first attempt.
And right now, only diamonds are mined in the seabed, or anything else. Titanium, tungsten, I don't know.
Yeah, so
with these dredging technologies.
Again, so there is mining on the seabed in national jurisdiction, and I was mentioning the diamonds offshore Namibia, in South Africa, for example. There was tin mining in Indonesia. It goes back and forth. There was an application for doing phosphorite, so phosphate in New Zealand, which was stopped by the government. But as I said, that's outside ISA's responsibility, because this is all governed and controlled and organized by the individual countries, right? So there's, besides diamonds and some dredging for titanium, and eventually tin and tungsten, depends a little bit. In Malaysia and in Indonesia, there's no seabed mining yet, to my knowledge.
Yesterday we were on this raw materials week, and there was a lot of discussions about this not in my backyard syndrome.
Yeah.
And I think that putting mining in the middle of the ocean could get rid of that problem. Maybe not completely, but
Yeah.
I see future here.
I think the first step should be that we all appreciate that our modern world is not working without mining, right? I mean, there are arguments that we stop all mining. Oh, yes, that's right. But this would mean that we would draw our talks on tables on the wall, for example, right? And there was a nice publication just last week or so talking about the CO2 emissions of the server systems for internet, and it's the same. It's by chance, but it's the same amount as we produce CO2 from food production, for example. So anyone is blaming eating meat, and it's bad for climate and CO2 emissions. But our use of the internet, I mean, just what we do just now is producing the same amount of CO2. And nobody talks about it because that's needed, right? I don't need to eat meat, but I need my server system. So we have to rethink, I think. All of us need to rethink, especially in wealthy societies. Not so much in poorer countries, because, I mean, they don't have access to servers anyways, right? I mean, they're not the problem, we are the problem.
Okay, so you can discuss
I have a
later.
question for the end, but I need to say now, because I want Ulrich start to think on that. Yes, why the countries are not mandatory, is not mandatory to follow the rules of the International Surveillance Authority for the area in national jurisdictions, because it exist frontiers for these and countries, and if the rules are different, the impacts are different. And the question is, why is not mandatory to harmonize the rules in national jurisdictions and these? For the next.
Should I answer now, or we can keep it for the end, right? Because it's more fundamental.
To the end. Yes, to the end.
I can answer it.
It's time to go to the coffee now.
So we'll have a short break of 20 minutes and we'll be back. Hi, so we're back again and we will start with the next speaker, that is Dr. Supong. He's a principal researcher at Korea Research Institute of Ships and Ocean Engineering. He majored in naval architecture and offshore engineering at Seoul National University, receiving a bachelor and a master. He holds a doctorate for offshore engineering from Technical University of Aachen. Okay, the floor is yours.
Thank you, Paula. I have to share my time. Okay. Thank you very much for your kind introduction. My name is Supong. My institute, Korea Research Institute of Ships and Ocean Engineering, is also a non-profit research institute like INESTEC, supported by Korea government, not fully, about 30%. And Korea is one of the 7 pioneer investors for CCFC. So my institute was responsible for development of mining technology for polymetallic nodules from the Pacific seafloor area. I was the project manager for 21 years from 1994 to 2015. That's the reason why I'm here today. I'm very grateful to be a speaker in this workshop. Together with my various role in my institute as a director, for this 21 years, I was started with from the paperwork to these large-scale sea trials. Today, I want to share my experiences and show my idea towards the sustainable mining of deep sea minerals. Yeah, global sustainability. Today, the weather is not good here, but we want to be sustainable in our lives. Yeah, it is the demand of critical metal is growing. The polymetallic nodules as a supplier for battery metals, the value has been changed much higher. As Ulrich introduced, the 3 major deep sea minerals are diverse and dissimilar in topographical characteristics. The first, the polymetallic nodules, are explored over 40 years. We have a lot of data, and we have defined what is hindrances, and the resource amount is, I can say, it is countable. And the most big advantage is the deposit is almost 2-dimensional, spread over the seafloor. Just we can harvest the nodules, of course, eco-friendly, up to the surface. It is a starting point of my research project. On the other hand, the seafloor massive sulfides is a 3-dimensional deposit. It's very local, concentrated, caused by hydrothermal activities, so that it is not easy to estimate resource amounts. Then the seafloor terrains are so irregular, site by site, so we cannot identify this is this. Here, there, all things are different. And the changing of terrain is inevitable through the excavation of the ore body. It's a big difference. The third resource, cobalt-rich polymetallic, the ferromanganese crust, is covering the seamount 2D plus 3D, which is 5D, or I think it is very, very hard to assess the resource because the thickness of the crust are not uniform. And furthermore, it's really, really hard to access to the slope of the seamount, how to keep on the seamount or the slope of the seamount. Not only the skyat or terrace of area of the seamount, just the most part of the crust is on the slope area. So that I think it is really hard, really challenging work to access the slopes. And furthermore, if we look at the dredged samples, then the crust and base rocks are together. It is not easy to separate cleanly only the crust from the base rock, so that we have to need additional separation, the crust layer from the basalt rocks. So the excavating separation is more problematic. Yeah. Today, I have seen the film of the metals companies, the campaign. The mining activity is conducted in sequence, collecting, lifting, onboard treatment, and tailing discharge, and offloading and transportation to the land. In this mining operation, we are talking about potential environmental impacts, habitat removal, and sediment plumes spreading out, water column and benthic area, noise and lights, and etc. How to assure the sustainability? Do we have to keep far away from the resource? How to assure the sustainability? In my opinion, I can itemize two requirements. In deep seabed mining, the sustainability focus on the impact by mining operation itself and the resulting potential harms to the ecosystem in benthic area and water column as well. So that the environmental impacts are caused basically by benthic intervention or disruption and materials transportation. The primary concern of seabed sustainability is the size of the mine site. As Ulrich mentioned, the area itself registered in the ISA is not whole, compared with the whole ocean sea floor, just very tiny parts. However, nevertheless, we have to limit the mine size, the area of the mine site. This equation says static sense, the size of the mine site is AR is annual nodule production area rate. It is dry tons per year. And D is duration of the mining operation divided by AN is average nodule abundance in the area. And E is overall efficiency of collector, and M is minable area. The overall efficiency of collector is, if it is higher, then size of the mine site is smaller. So in the sense of benthic intervention, the overall efficiency of collector is multiplication of dredging efficiency by area sweep efficiency, ED multiplied by ES. So as we have seen before, the higher overall efficiency, the smaller the size of the mine site. The enhancement of sweep efficiency, therefore, reduces the size of the mine site. For instance, if the ES is improved from 60% to 80%, then the reduction of the mine site is 25%. It's big gain. So that the performance of the collector is one of the key factor for sustainability in sense of venting intervention. As here summarized, enhancement of overall efficiency requests the optimum design of a collector machine or robot. Not just straightforward. The mineable area is not the straight soccer playground. We have to delineate the mineable area. We have to design the mining path optimally so that the collector vehicle has to be capable of following the complicated path. And furthermore, the control algorithm for path tracking is essential one based on high precision C4 navigation system. All the collecting operation cannot be controlled by manual. It has to be optimized. On the left-hand side, on the right-hand side, you see this character. It is Korea, not KC. And we have tried to follow this path by mining robot. You will see that in the next slide. So that we have tried to make collector from machine to robot. Started with test bed mineral 1, its first generation. We have conducted C-test 2009, 2010. It is the goal of this C trial is evaluation of the concept, the acquisition of data as well. As you see, this tiny, small, cute machine is mineral 1. However, it is already 10 tons heavy. We have tested 1 month very complicated path. How can move this collector vehicle on the soft sea floor to get the data. Based on this first testbed experience, we have extended to design and construct higher scale mining robot. It is named Mineral 2. It is the TC test conducted 2012, 2013. The target of this test was the validation of operational ability and the collection of design data for commercial system. On the top side, figures shows the Mineral 2. It is a combination robot of 2 identical robots. Left-hand side and right-hand side. It's just combined as a combination robot. We have adapted this combination robot concept because the width is wider than 5-6 meters. Then it is not easy to transport on the highway. So we have divided into parts and combined on the key of the port. So we have tested nozzle collecting performance, and the more important purpose was verify the control algorithm for path tracking. Now we are waiting for commercial system, Mineral version 4. Mineral 2 is two identical robots are combined. Mineral 4 is 4 units should be combined. I'd like to repeat again. Mineral 2 is from simply remote control to automation. The fundamental functional requirements are first, the structure must be strong enough, but not heavy. The specific strength is required. At the same time, the specific strength of the robot is important because for the optimum contact pressure on the seafloor. If it is too heavy, then it is not available to move forward. It is too light, its trafficability is not enough, high enough. So highly efficient and robust nodule pickup device and crushing and disposing device and launch and retrieval system, real-time remote control and high precision underwater navigation system, and so on. Those are fundamental functional requirements. Based on this functional, we have to put the algorithm for path control automatically. Automation is essential to enhance the overall efficiency. No operator can watch the screen and all control. And the second plume is to block the visibility totally. We are all blinded, so that the collector must be capable of tracking well-designed mining path. And then reversely, the mobility of collector vehicle itself provides designability of the optimum mining path. Good car, we need good car. So that in in-house course of real-time dynamic simulation of the collector vehicle, real-time dynamic simulation, and multidisciplinary design optimization framework and algorithm of path tracking were used for design and control of Mineral 2. It was very successful. As you see here, Mineral is crossing over the track made by itself before. The Korea, the world is changing the color from white to red. The total distance of this Korea is 1.5 kilometers. We had to wait 1 hour, 40 minutes just looking at the screen. It was very interesting. Yeah. The second factor of sustainability is the materials transportation. Our purpose is produce the nodules, ore, but together with seawater and sediments, in order to produce the ore bodies as much as possible for unit time, the volumetric concentration must be higher. But we have limit of the higher volumetric concentration. If you think the highway, a lot of cars are running together, then it's very dangerous. So that we have to find out optimum volumetric concentration. However, if it is too low, then energy consumption is too high. It costs too much. It is too high, it is dangerous. It is very risky for pipe clogging, or structural damage, or pump system as well. So that if we can find out optimum volumetric concentration, we can gain the cost reduction in CAPEX and OPEX as well. And at the end, the byproducts and tailing can be reduced. In my project, I have adapted buffer station as a intermediate storage and heating station, because the first collecting procedure cannot be kept constantly. The seafloor moving speed is controlled constant, and nodule abundance is not homogeneous, so that it is inevitable this fluctuation of collecting amount, so that we have to regulate the production rate. This is the role of the buffer system. Is a flow assurance, and at the same time, at buffer station, we can push out the sediments as much as possible before we lift the nodules to the surface. Oh, sorry, it was backward. Yeah, the optimum volumetric concentration concerns about production of the nodules. However, we have byproducts, seawater and sediments as well. In order to achieve the annual production of the nodules, we have a lot of seawater and sediments together. So that, in my opinion, we have to find out the balanced capacities from nodule production to seawater treatment and tailing and offloading and transportation. All these four major procedures are conducted simultaneously on the surface platform. In my opinion, the treatment of byproducts is another key for commercial mining. It's a schematic diagram of the left-hand side figure. The slurry flow is this nodule, sediments, and seawater. The slurry flow has come up to the surface, then ore, seawater, sediment has to be separated in two stages. Then ores are conveyed into the storage cargo space, and the other parts, the byproducts, have to be collected and treated eco-friendly. If the regulatory requirements are too high, then we have big problem, big headache. How to make the mass flow smoothly without congestion and clogging on the surface platform. It is a challenging work, I think. So everything, the materials have to flow smoothly. Nodules are stored in the cargo space and uploaded to the transportation vessel, and the rest have to be pushed down in the thermocline water depth, below thermocline water depth. Otherwise, the ship will be flooded and sink. In commercial scale, for pilot scale mining test, we have a solution. However, for commercial scale, we have to find out sophisticated design of this mining platform. It is my story. The lifting riser, original plan was 2,500 meter long. For one pump unit, then two pump units are used for 5,000 meter lifting. But the budget was not big enough, so that I had changed the plan. This figure shows the 2,500 meter vertical riser is truncated to 500 meters. And at the time, the pressure drop occurring in the vertical riser of 2,500 meter is artificially made on board with this purple colored pipeline. So it was tested at the end of the riser. The buffer station was connected. In buffer station, we put the artificial nodules before and we have lifted. It was alternative method. This slide shows the photo gallery. It was 2016 December. The vessel come to the port the Christmas day. This Norman Baltic, it is chartered, multi-purpose vessel having moon pole and crane. All the other parts were constructed, designed and constructed, put on board and integrated together. Yeah, it was my story for polymetric nodules for 21 years. After 2015, we have continued the not national project, but internal project, my institute. As the background proposes to apply for SMS. For SMS or cobalt-rich crust, there are problems. The environmental perceptions are very, very limited. Just looking through the screen, the visibility is very limited, and if the mining operation is started, the blooms are blocking all the visions. So that environment perception, how to enhance this environmental perception mobility. The mobility and stability is different from the seafloor polymetric nodules. SMS and seamounts, the mobility and stability is quite different. And third problem is, in my sense, the most severe problem. Everything is absolutely dependent on the operator's skill, operator's ability. Therefore, the approaches have to be found out. The first collector vehicle have to be designed simple and smart and robust, capable of moving on the very irregular seafloor or even the slope. And to enhance the environmental perception, we adapted digitalization of the whole system. Environment and operation condition, digitalization. The next slide, I will explain a little bit more. If we can enhance the operator's perception through the vision and hearing and kinesthesia and the haptics, and then the operator can recognize the condition much better. Then after this recognition, he can decide better action plan. This is the approach. In this sense, we call it HILS, a human in the loop system. As summary, I named this is operation in CPS, cyber physical system, shortly CPOS, cyber physical operation system. I was asked to limit my presentation 20 minutes so that I could not put more slides. It is just one slide. This cyberspace and physical space and they're interacting together. through the interface, haptic device, motion seat is cockpit. This basic idea is the operator is feeling as if he is sitting in the machine, robot, virtually. And he feels the dynamic reaction of the robot on the seat floor. The feeling can enhance the perception of the operational system, operational condition, and environments surrounding condition as well. So this is a perception, cognition, decision, action. These kinds of loop can be learned, machine learned, or if we have sufficient countable database, then afterwards, the partial autonomy can be expected as well. This idea is inspired by Vamos project as well. So my team is cooperating together with INESTEC researchers, Jose and Almeida together. The next slide will show you the video clip. This CPOS is bottom side is a real physical space, upper side is cyberspace. Let me show you. Oh, just a moment. The sound, together with sound. This is cockpit of operator.
I buy one. You do.
How much is it?
A lot.
Left hand side is physical system, the right hand side is cyberspace. This cyberspace is only possible together with real-time physical engine. The operator is working together with haptic device. The great advantage of this CPOS system, we can analyze the performance of the robot and where is the fault, potential fault before the accident. And the other one is, as this video shows, if the forward terrain looks dangerous, then the cyber robot can move forward before and check whether it is safe enough. Then if there are danger of overturn, then we have to change the plan. For instance, target location, we have to find out the safe path, like a climber of a mountain. It is a real-time physical engine, engine's powerful performance.
Why don't you just lift it up?
Pardon?
Why you don't just lift it up to another?
Such a downtown is very cost consuming, time and money.
Okay.
Yeah. And based on this simple system, the multiple robots can be collaborative work together. We have now 3 years research, first phase, 3 years first phase this year, and the next second phase is for 2 years more. It's altogether 5 years project. Then, based on this evaluation, it can be decided further research or stop.
Don't stop.
Don't stop. Don't stop.
I don't see the collector. I see the cutting machine. You cut, But the collector, you have a second machine to go and collect the material to pump, or is this?
Yeah, it is lab scale robot.
I know, I
Yeah,
understand.
after the lab scale research work, we have planned to go to the sea
Okay.
as.
But the collector is, collecting material is not in the same machine, if I understand.
No.
No, is it a different machine? They coming and collect material to pump?
Yeah.
Okay.
So I would like to say the sustainable mining is profitable. Why? The first, eco-friendliness, minimize the benefit intervention and suppress the byproducts, and it means the reduction of CO2 emission. And the safety is nothing, it is no worth to say again. Profitability, saving cost for sediment water treatment, and saving cost for pumping operation, and saving cost by downtime reduction, and maximizing performance of miner robot. This sustainable mining is not the hindrance of the commercial mining. It is what key of the profitable mining. This is my opinion. Last but not least, most important for sustainable mining are cores. C is cost effectiveness, O is operability, R is reliability, E is environment friendliness, final S is based on safety. Thank you very much for your kind attention.
Thank you so much. It was an awesome presentation, and the previous presentations and yours, I'm sure that the final discussion will be awesome. And Chris van Miegen will also contribute to that. So Chris is our last speaker, last but not least. Chris is the Managing Director of Global Sea Mineral Resources at DEMA Group. His background is in engineering, and he has a PhD in applied economics. For the ones that don't know, he is really active and participant and presenter in meetings with regional and international intergovernmental bodies charged with regulating the marine mineral sector. He has spent the last 20 years overseeing marine engineering projects across continents and has a track record of successfully balancing economic, environmental, and social considerations for sustainable growth. Today, he heads a team developing ultra-deep ocean technologies, focusing on recovering critical metals needed for sustainable development and ultimately for the future benefit of humankind. We are all excited to hearing from you. Chris, the seafloor is yours with a presentation entitled Meeting Increased Metal Demand in the Most Environmentally Responsible Manner.
Thank you. Thank you, Anna, for giving me the floor, and thank you for inviting me to this wonderful conference. So let me dive right in. So you'll see, contrary to what SUP is using in sustainable mining, I use responsible mining. And this is a small difference, but I mean, sustainability over the past, I think 10, 15 years has gotten, I mean, everybody is using the word sustainability, and it's being used in so many different connotations. And it also means a different thing for a lot of people. So instead of going into the argument, is it sustainable? Because the first thing you will hear is mining is not sustainable. So the way to overcome that is by using, I believe, responsible, because we have to agree that it remains an extractive industry, and the word sustainability with an extractive industry is just asking for problems with your stakeholders. So we have moved on from that, and I speak out of experience, because we used sustainability in the beginning as well, but now it's down. So what does it mean, responsible deep seabed mining? I will talk about these different topics. I will give an introduction. I will talk about our future, but I'll keep that brief because many of the presentations today already touched on this topic. Then from a responsible perspective, I will touch on the geology, the technical, the environmental aspects, the regulatory and economic aspects. And then finally to conclude with a schedule on how far we have progressed and what is still to be done. So on the introduction, so GSR is a 100% subsidiary of the DEME Group, and the DEME Group is a Belgian dredging contractor, which is 140 years old. Our core business has always been dredging and land reclamation, but since 20 years we have evolved due to diversification strategies into the offshore wind industry. So we are one of the largest, if not the largest, installer of these offshore wind turbines. We started this industry 20 years ago on the Belgian coast by getting a concession on the Thornton Bank, by talking to regulators, by talking to the environmentalists, getting feasibility studies, environmental impact studies done, developing the technology, finding partners, and proving that that offshore wind is actually a feasible industry. And it has taken us many, many years to do that, but now we are proud to say that it covers almost half of our turnover. So it's that same philosophy of being in the long term, being able to look far into the future and being able to say, okay, we do this step by step. We will develop the industry, not to sell electricity in this case, or not to sell metals in the case of deep sea mining, but simply to show that it can be done responsibly, kick off the industry, and once the industry is mature, basically what we do with our offshore wind is we are a contractor, and we provide these services to these large concession holders that want to build these wind farms. So $2.5 billion turnover and around 5,500 people work in the DEME Group. As I mentioned, the core business is dredging. So here you see in the Suez Canal in Egypt, 3 of our vessels widening and deepening the Suez Canal. And why do I show this? Is because we're transporting sand, rock, clay. That is really what we've been doing for so many years. And it's not that different with polymetallic nodules. It's all about hydraulic transport, pumping something from A to B. Here you see another type of our vessels. It's a trailing suction hopper dredger in Panama, widening the Panama Canal. So as I just mentioned, we have diversified in the offshore wind, and first from a European perspective. So you see all these locations where we have contributed to placing these turbines. I believe we have already installed 2,400 of these offshore wind turbines, and we are now exporting this product, this service, to the US, to Taiwan, to Japan, and basically globally. So on a global scale, we work, it's not that good to see on this screen, but better on my own screen. You see all the places that we work globally, but the reason why I'm showing this chart is because on the left-hand side, you see these 2 locations in the middle of the Pacific Ocean. The top location is the Clarion-Clipperton Zone, and the bottom location is the Cook Island Exclusive Economic Zone, where we are also looking at exploring for these polymetallic nodules. So that's a little bit of an introduction on the DEME Group. As I said, it's my parent. Global Sea Mineral Resources was set up around 2012. I've been working on seabed minerals for the last 12 years full-time, from 2010. And I'll talk a little bit more about the concessions and the concessions with the Seabed Authority in a minute. But first, why is DEME interested in seabed minerals? So, you know, the sexy story is batteries and low carbon energy, but the less sexy story, but the truth and the major driver is urbanization. And the fact that we have an increasing global population. I think yesterday we hit 8 billion people. They celebrated the fact that we were 8 billion. Well, those 8 billion people, they need to live somewhere. Luckily, the most recent scientific paper is saying that we will not reach the 11 billion that the UN is predicting, but that we will actually top off at 9.7 billion around 2064. That's good news because it means we will soon go to a more equilibrium. So by 2100, instead of 11 billion, we'll be again at 8.8. So not much more than today. So that's good for nature, I would say. But 66% will be living in cities. And if you do a back of the envelope calculation from these 1.7 billion additional people in the next, say, 40 years, then you need to build a New York City every 11 weeks. So that is just mind-blowing, the number of, infrastructure that needs to be built, and obviously the metals that go hand in hand with building that infrastructure. So on top of that urbanization and global population growth, you see obviously climate change. And we have touched on climate change since 2017. It's been a hot topic, for example, the relationship between climate change and critical minerals by the World Bank. Their first report appeared in 2017. They updated that report in 2020, including the aspect of recycling. And obviously the landmark report of 2021 from the International Energy Agency, showing that the difference between a conventional car and an electric car with regards to with critical minerals, but also the production of energy, how it's being produced, comparison between traditional energy infrastructure versus this low carbon energy infrastructure. And you see a multiple of metals that will be necessary. More precisely, if you want to be net zero by 2050, you will need 6 times more metals than we have today. Even more precise with regards to cobalt, nickel, manganese, and copper, because I zoom in those metals because those are the ones that are found in polymetallic nodules. You see these multiples ranging from 2 to 21, which obviously puts us to the question, where is it all going to come from? And if we look at where it's today coming from, you see obviously a rapid decline of the ore grades in land-based deposits, which reflects in the energy requirements that are necessary to extract those metals from land. So the more energy you need to put into it, the higher your carbon footprint possibly is, and also the interaction with water. So while ore grades decline, the impact on our society increases. So that same EIA report concluded that by 2040, 10% from the primary supply can come from recycled metals. So while we are fully aware and promote the circular economy, it's a fact that we don't have enough material in stocks. So we need to have access to other supplies, what we call a diversification of supply. So today mining, already land-based mining, already influences 50 million square kilometers of the Earth's surface. This is a paper from Laura Sonter, Australian academic, and she looked at how the increasing impact of land would impact biodiversity. And actually she is saying these new threats to biodiversity may actually surpass those averted from climate change mitigation. So this is like a paradox. On the one hand, we call it the sustainability paradox. So on the left-hand side, we know that climate change leads to biodiversity loss, but we also know on the right-hand side, to prevent climate change, we need mining, and mining also leads to biodiversity loss. So it's really about which is the best, which one is the best we need to follow. So we conclude there's obviously a need for responsible mining solutions. And then it basically boils down to trade-offs. If you want to talk about what is responsible, then you have to start making trade-offs. So here you see our globe, and there is this paper. This is the paper from Laura, and she maps all the land-based mines globally. The one with a darker color are the ones that are associated with metals we need for the low-carbon future. So these are all the mines you find on land. And then we have another paper from Dinnerstein, and Dinnerstein concluded in 2020 that we need to protect this part of the globe, which is this part of the landmass, which is more or less 30% of the landmass, in order to reverse biodiversity loss and stabilize Earth's climate. Now, if you would zoom in, it's impossible on the screen, but if you would zoom in, you will see that obviously those green patches are next to the mining areas. They're not overlapping. It's not that they're saying we need to close those mines because that won't make sense, but they're saying we need to protect these large swaths of the planet in order to reverse biodiversity loss and stabilize Earth's climate. Now, you've heard about protecting 30% of the oceans by 2030. This is a call that is being made by the BBNJ, but also by Greenpeace, by the Blue Leaders here in Belgium, where Belgium is one of the founding partners. Well, they've done similar studies for the ocean. So this is the first study by Sala, who said this is a near shore. He said if we protect all these patches of the ocean, we have that same, reversing, we maintain biodiversity, we stabilize Earth's climate. We've done something similar for offshore. This is the study that was commissioned by Greenpeace to Oxford, and to say, okay, what if we want to protect 30% of the high seas? Which parts do we need to protect? And this is the outcome. You see in dark blue, this is what we need to protect. So now we know what we need to protect on land and what we need to protect on the ocean, which is 30% on land, 30% on the ocean, in order to protect biodiversity. So left-hand side, watch very carefully, left-hand side of the planet, here you have the Clarion-Clipperton fracture zone in dark blue. This is the exploration areas. So we all know that exploration does not lead to exploitation. It is just exploring where the nodules are and then identifying these patches, minimizing the areas that will be impacted is basically what we're doing. We're trying to identify where are the patches with a high abundance of nodules. There's an economic cutoff grade that if you go below this economic cutoff grade, your vehicle is inefficient. If you go above, you maintain production, you're being efficient. So these patches we need to find. So if I add one more, then if you say that 50%, which is very, very aggressive, I don't think it will be 50%, it will be more or less 30%. But let's say it's 50%, then it's even half of what you saw in dark blue. You may see that, again, it's not overlapping with what Greenpeace and Oxford have concluded. What actually they did include are the areas that were mentioned earlier, what's mentioned, the areas of particular environmental interest that are around and in the middle of the Clarion-Clipperton fracture zone. They are included because these are no mining areas. So this is, we have to look at this as trade-offs. If we are not impacting biodiversity to the extent that we are not impacting these areas that need to be protected, the metals need to come from somewhere. So that brings us to a conclusion on this chapter on responsible supply. On the left-hand side, you see an offshore operation. On the right-hand side, you see a land-based operation. Both would deliver nickel, cobalt, copper, and manganese in obviously the case of polymetallic nodules. And they both can be recycled. Metals are recyclable. Now, what we have done, we have published a life cycle assessment earlier this year, January 2022, that looked at the cradle-to-cradle life cycle impact of producing the same amount of nickel, cobalt, copper, and manganese from the ocean versus the average land-based mine. And we have concluded that we can do that with 40% less carbon. So that is already significant. We're changing the entire global car fleet because electrical vehicles produce 30% less carbon than an internal combustion engine. So if we can do that for the entire car fleet, there is a similar reason to do that for some of the metals as well. Not all, because there's good land-based mining as well. But what we are seeing today is that the new land-based mining is going into very highly diverse areas, biodiverse areas, very political and stable countries, and so forth. So this leads me to conclude that there is preliminary evidence that seabed minerals, and particularly polymetallic nodules, can be a responsible supply for metals. So that brings me to the 5 topics that I will dive into. So first of all, the geology. So Jim Hine from USGS, he wrote this nice paper back in 2012, and it was more or less republished in Nature in 2020, where he concluded that the nodules in the Pacific Ocean contain more manganese, nickel, molybdenum, and cobalt than the entire terrestrial reserve base for those metals. So that is huge. That is very significant. It means that whilst the resource is there, we need to come up with responsible technologies to access these resources. That is really the key to unlocking this deposit. So where are those nodules found? In the Clarion-Clipperton fracture zone, we've touched on it. Left-hand side is Hawaii, you see the island. Right-hand side is the coast of Mexico. In green, you see 3 patches more to the east. And those 3 green patches are basically the concession that we have been awarded in 2013 by the International Seabed Authority. And since 2013, we've been organizing 7 expeditions, or we have organized 7 expeditions to the Pacific Ocean, to our concession area. And we always do 3 things. We do resource definition, so where are the nodules, what is the grade, what is the abundance, etc. We look at engineering data, how can we responsibly collect these nodules, so we develop different types of technologies and we test them over the different expeditions. And we continuously deploy monitoring devices that will create an environmental baseline. Because at some point, as we did in 2021, before you can do an actual impact test, you need to know what the environment is beforehand. So we've been doing that for many, many years so far. So for the first one, the resource definition, how do we do that? Simply an AUV flies over the seabed at 5 meters height, takes pictures every 2 seconds, and establishes as such a photo mosaic of the seabed. And these nodules, as you have seen in previous pictures, they're on the surface, so you can easily see the nodules. The thing is, we don't know at that point in time how much is below the sediment and how much is above the sediment. So what you need to do is this step-by-step process where you take pictures and then calibrate those pictures with in situ box scores. So a box score is basically a device that goes to the seabed. It takes a 0.5 meter by 0.5 meter sample from the seabed, 0.5 meter width and length, and also depth, brings it to the surface, and then you look at the correlation between how much of the nodule is above the sediment and how much is below. It's sometimes 1/3 above, 2/3 below the sediment. So with that correlation, then you can say, okay, in that picture, you use software to actually calculate the volume of the nodules. And this is a very simple process compared to, for example, seafoam-massive sulfides or even land-based deposits, because those are 3D deposit, whilst ours is a 2D deposit. It's really conventional. It's time and money. You send an AUV over these patches of nodules, and you spend this much money, this much time, and you will know that you have identified this amount of resource. So that leads to this map. You will see in detail here that we have obviously identified first where there are seamounts. So in red are the seamounts, where we obviously want to avoid. We want to go to patches that are flat. And then for the patches that are flat, we have done these different surveys, and we have identified patches and preservation impact areas within our exploration areas on future mining opportunities. And from this, I'm saying 20% is actually mineable, right? So earlier I said 50%. I mentioned that it was very aggressive. Here we're saying 20% from our concession area is actually mineable. And mineable doesn't mean nodules are there. It means sufficient nodules are there. Again, above 10, 12 kilograms per square meter. Everything below we leave behind. So again, the ecosystem associated with those nodules below 10, 12 kilograms per square meter, we leave as is. So that brings us to the next chapter, which is the technological considerations. So you've probably seen these types of animations many, many times. You will have a mining vessel, you will have a bulk carrier going up and down, you will have support vessels, but the mining vessel will have a riser to the seafloor with a collector vehicle on the sea. And when this was made back in 2013, we said, okay, what is the most important aspect, similar as Supong? The collector vehicle is obviously the most critical part in this project. It has the interaction with the seabed, it determines the production, it determines the environmental footprint, so it needs to be well designed. So this is a commercial vehicle, commercial size vehicle, and if you look at it, if you tear it down in 3 aspects, it's really propulsion, trafficability, how do you drive, it is how do you pick up the nodules with the collector head design, and then how can you make it auto-adaptive so it basically becomes a Google car, as Soep already showed. So instead of building it in one go, we said we're going to break it down in the propulsion aspects, then the pickup aspects, and then obviously the bringing the nodules to the surface. So in 2017, we built a first robot, we call it Patania 1. And we built it in 2016, and we tested it in 2017. But we went to our concession area at 4,500 meters water depth, where the nodules are. Because as Soep also pointed out, in this question about trafficability, it's all about the bearing capacity of the soil. If your vehicle is too heavy, it'll sink in. If it's too light, it'll move forward. So no better way to test it than in situ in the Clary-Clipperton zone. So the vehicle was equipped with buoyancy elements, so we could actually take the buoyancy elements off or on and play with the weight of the vehicle on the seafloor. And as such, we determined what the ideal weight versus bearing capacity of the soil was. We did that in 2017. That led to the design of Patania 2, which is a much larger vehicle, a 35-ton vehicle, but we knew exactly how much buoyancy to put on it for it to behave accordingly on the seafloor. And here you see that it also included a suction head. So that suction head we developed in a lab here in Antwerp. And that was then all integrated in Patania 2 and tested in several times, but ultimately in 2021, which I will talk about in a second.
Continue because the people outside.
Okay.
Yes.
And then we have this test leads to sufficient data for us to design what we call Patania 3, which then will be the commercial vehicle. And this commercial vehicle, to give you an idea on size, here you see what the mine truck that operates on land. It's similar in size, we only need one, whilst on land you need 40, 50, depending on the open cast mine, to remove the overburden to access the resource in the soil. So this is the plan for the future. We call it a precautionary approach. It's learning by doing. It's step by step what most companies are doing. So here you see Patania 1 tested on land. You see the buoyancy elements on the right-hand side that could be put on and put off. And then it was deployed to 4,500 meters. We investigated trafficability, sinkage, slippage, bearing capacity, turbidity, etc., etc. And then from that, we went into the lab and we designed first with CFD, but then with actual lab tests, the suction head. So here you see a 1 meter section of the suction head that for 3 months went up and down into this laboratory to find the right balance between the energy that goes into it and the efficiency of picking up the nodules. Because it's based on a Coanda effect, what we're doing is we're jetting above the nodules. We're jetting water above the nodules, 10 centimeters approximately, which creates a vacuum and lifts the nodules into a flow of water into the vehicle itself. The vehicle will then disperse or distribute or separate, the nodules from the sediment. The sediment goes back to the seafloor and the nodules are at this stage stored in the vehicle, but in the next stage, Patania 3, they will be lifted to the vessel. So there, as I said, both trafficability and pickup were integrated in Patania 2. And here you see Patania 2 with a custom-built launch and recovery system going offshore again to the Pacific Ocean, to the Clary-Clipperton zone, 4,500 meters. And last April, May, we did 15 dives, and I think more or less the vehicle drove 156 kilometers on the seafloor. So that led us, we installed, call it selfie sticks on the side of the suction head, many cameras on it, but the video I will show you in a second is the video of those selfie sticks, because we wanted to zoom in on what is now happening on the seafloor and how are those nodules being lifted from the sediment. So this is a picture of the vehicle on the seafloor on the 10th of April at 4,400 meters with all the cameras you can imagine and sensors you can imagine. So here is the video. It's a 30-second video. First, you will see a little 3D animation of the process itself. And then secondly, you see how it played out in real life. You will see that the nodules underneath the suction head are lifted gently, but the nodules 20 centimeters next to the suction head stay in position. Let's see it as well. So you see, it's let's see. So you see, it's not digging. It's not invasive. Obviously, there is an impact, but we try to limit the impact make it as small as possible. As I mentioned earlier, the sediment and the nodules is separated in the vehicle. So the more sediment you pick up initially, the more sediment will come out of your vehicle in the back, obviously. So from the study we did last year, we now can conclude, you see this second vessel in the background. This is a vessel from JPI Oceans. It was funded by the EU. It had 25 scientists on there, 9 different countries. They were deploying lots of equipment, which I'll show in a minute. But they have, amongst others, we have and they have studied how much sediment we actually picked up around the nodules. And we conclude it's between 3 to 8 centimeters. So it's very little sediment that is actually being picked up because this suction head is so well engineered that it really, you can go in with lots of energy and pick up 30 centimeters of sediment together with the nodules, but that obviously would create a very large turbidity plume. So by limiting it to 3 to 8 centimeters, we really limit the amount of sediment that gets into circulation. So talking about the environmental effects, we see obviously 4 major impacts. The first one is the removal of the hard substrate. You're removing the nodules, and they are the base for some of the sessile fauna. Now remember, sessile fauna is sessile fauna you can see with your own eyes. And if you can see it with your own eyes, sessile fauna, it means that it is megafauna. And the megafauna, we'll talk about it in a second, is less than 1% of the biomass in the deep sea. Remember, it's 85 or 86% of the biomass in the deep sea are microbes. But nevertheless, the substrate or the nodules, they are hard substrate for some of that sessile fauna. Now, as I mentioned before, we need to solve that problem with spatial planning because we need the nodules. We need to realize that we will take away the nodules and we will take away the sessile fauna associated with the nodules. So once the nodules are gone, the question is how many nodules leave behind, and you solve that with spatial planning, with reducing your impact area as little, making it as small as possible, and leaving enough nodules on the seafloor so that ecosystem is protected. Then you have direct impacts such as noise and light. That is an engineering issue. We need to understand from the biologist what is maximum allowable, and then it could be engineered. Now, we have measured during our test last year what the sound impact was, and preliminary, there's a paper in peer review, but preliminary results show that at 400 meters, it is almost nothing anymore. What we're hearing at 400 meters are the ships and not anymore the collective vehicles. So that is, or collective vehicle. So that is also promising, but I look forward, I haven't seen the details yet. I know some of the preliminary results. And then a third direct, but now we're also moving in the indirect impact, is the turbidity, because the turbidity can obviously be created locally in the mining area, but it can also be drift into the non-mining areas. So here we have studied extensively how this turbidity plume travels through the water column, and I'll talk about it in a minute. But you have turbidity that's created on the seafloor, but as well as from the return water. Now, it hasn't been decided yet where the return water needs to go. Our plan A is to bring it back to the seafloor to make sure that actually the sediment lands in the mining area again. But further tests need to be done there. And then a final indirect impact is obviously the carbon footprint, and there is preliminary data indicating that it can be 40% better than land-based mining. And a point I forgot to mention earlier, when I said 40% better than an average land-based mine, well, I did touch on it. That is the fact that today's new land-based mines, and specifically Indonesia, for example, for the nickel laterites, they are in a super high carbon intensive environment. So not only because they're in Indonesia and the energy infrastructure from Indonesia is coming from coal, but also because they are trying to use a nickel laterite deposit for high-grade nickel for batteries, which means a 2-step processing step, which means double the amount of carbon. So we are not only 40% better with the average mine, but we are in the order of 70–80% better than actually the new nickel mines on land. So a little bit focus on what is the biodiversity. A lot of it is microbes. This is a bit of the microfauna and macrofauna. In the middle, you see this eDNA tree that is being used to compare the different species in the Belgian area with the French area, with all other areas, the Chinese areas, because the scientists have concluded that if you do this only visually, there is simply too much confusion about what is what. But if you do it on a DNA basis, then it's very clear, and you can actually, if you would zoom in on this DNA, you can see certain species coming back in different areas. As mentioned, I think by Noemi, all the environmental data in the international waters is public domain. So this is being shared knowledge. It was knowledge. So here I talk about biomass, which is 80% microbes. I believe 2% meiofauna, and then another, 11% meiofauna and then 2% microfauna. And less than 1% is megafauna. So whatever you see on in news articles, whatever they say about an octopus or a fish or sessile fauna, an anemone or whatever, it's less than 1% of the life is down there. So in order to do the test in 2019, 20 and 21, we had to write an environmental impact statement, because if you want to do work in the international waters for this type of test mining equipment, you write an environmental impact statement. We did that and we published it in 2018. There was a stakeholder participation process organized by the Belgian government. Several comments were delivered by WWF, Greenpeace, etc., which comments have been reflected in the next version of the environmental impact statement. So it's still publicly available. Because our test was done in the Belgian area as well as in the, well, call it the GSR area with the Belgian state as sponsor state, and the German area, we had two environmental impact statements delivered. One for the Belgian area, one for the German area, and both are publicly available. So here you see two vessels in location and the different tools that were deployed in 2021. This is state-of-the-art, latest suite of technologies from different AUVs, different ROVs, etc., etc. And if we look at the seabed, this is more or less how it looked like. You had an impact area of those 3 lanes on the left-hand side, and you had different types of landers, sediment traps, ADCPs, all put in position before the test was done. Then you do the test, then they will remain in position to measure really the plume. The plume drifted in the currents. There's 2 major drivers that determine the direction of the plume. That is the current and that is the topography of the seabed. So depending on the topography, a plume, which is a gravity plume, will follow the topography of the seabed, and then on top of that, the current. So you can kind of more or less predict where the plume would go. And that is where you would then install these deep sea moorings in order to catch the plume. On top of the deep sea moorings, you had the AUV and the ROV that would fly through the plumes, again, to map where the plume would go and what the density would be. So we're very proud that in September 23, the first publication of this test came out in Science Advances. It actually was the cover story of Science Advances in that month. So, which is a high impact paper. I mean, impact is, I think, 14.7. So this is done by MIT, and they concluded that the majority, let's say 90 to 98% of the plume remained locally and below 2 meters. So as I explained, it's a gravity plume. It immediately goes to it remains on the surface and it settles in the vicinity of the mining area. What we haven't done at this stage is we haven't optimized the diffuser of the collector in order to, again, bring the plume closer. We haven't used the current to kind of keep, for example, imagine a mining plan in the future, the currents on the deep sea floor, they change. And if the currents change and you can predict where the currents are going, the vehicle can take that in consideration to keep the plume on the mining area. All these things are optimizations. We haven't included that. We first need to create the plume, measure the plume, then calibrate our theoretical models, and then you can use the theoretical models to actually start refining your process. So this is a major publication. Nobody reported on it. So everybody reports on, the papers that say we're going to destroy the ocean, and the New York Times and the Washington Post, they want to report on that. But if somebody, MIT Science Advances, nobody is interested. So it's a very frustrating process, but that's life. So then we come to the regulatory considerations. I won't talk too much about it because we have 2 representatives of the Seabed Authority here, but it's Few things to mention is it's got a long history, not necessarily the seabed authority, but the fact that we know about polymetallic nodules. There was also a Belgian professor associated with writing the expedition report of the HMS Challenger back in 1878. Fast forward to 1994 when the Seabed Authority was set up, incorporated, and then the first deliverable of the Seabed Authority was exploration regulation, which was delivered in 2001. And once you see this, this regulatory framework being delivered that allows exploration to happen, boom, you see this huge increase in science, because suddenly there is a regulatory framework that allows science to be done, that allows exploration to be done, that has a sight on exploitation, and people start investing. So you see science is heavily correlated with a commercial interest. The reason why we know so much about space is because there's a commercial interest in space. So you see that all these countries took concessions, exploration concessions, and we now are hoping. You see, this is an older slide. It says 2021 for the exploitation regulations. It's because it's been promised for so many years, but we can surely say it's not 2022, but let's say maybe hopefully 2023 that exploitation regulations will be delivered. And then the question is, a lot of countries, they say, or a lot of positions of NGOs say, we don't have enough science to adopt regulations. I think that's putting the cart before the horse. I think what we need to do is adopt regulations, and the regulations need to have all the science we need. And if you include all the science we need in the regulations, then you create a roadmap, a rule book, and only when that science is collected and reviewed and an EIA is accepted, then exploitation should go ahead. So it's not that we need more science to adopt regulations. What we need is regulations that will trigger this necessary science that would lead to a plan of work, which could or could not be accepted. It depends on how good the science is and how good the results are. So in international regulations, we've been part of that discussion for the last 10 years. Won't talk too much about it. What is interesting here is that you need national regulations as well. For a contractor to work in international waters, you need a national framework. So Belgium adopted in 2013 a national framework that would allow a Belgian contractor to work in international waters. And then in 2021, we adopted a resolution at the Parliament, which would support further research and also the precautionary approach in developing the exploitation regulations. And now, last year, our Deputy Prime Minister indicated that Belgium would become part of the Council as from 2023. Within the International Seabed Authority, you have three main bodies. You have the Legal and Technical Commission, who advises on technical issues. Then you have the Council, who reviews and provides a decision to the Assembly that then eventually needs to decide. The Assembly is the 167 member states. The Council is a body of 30 countries. And it's in that body that Belgium will be sitting as from next year, which is perfect timing because, as I just mentioned, hopefully next year we will adopt regulations. So final chapter before we go to the schedule. This is some of the economic considerations. So here you see metal prices for a polymetallic nodule have evolved over time. Mining goes up and down, while prices go up and down. It's a supply and demand issue. So on the left-hand side, you see that the value of a nodule and average is roughly $500 a ton for the metals that are contained in the nodule. It goes up and down. And what you see here is that obviously we are now in a we've passed the downtrend and we're in an upward trend due to the fact of this whole realization of critical minerals and the fact that looks like we won't have enough responsible sources for these metals. What does that do if metal prices go up? This is a cost curve. And on the left-hand side, you see the lowest cost producer of nickel. On the right-hand side, you see the highest cost producer of nickel. So on the x-axis, these are the volumes that are being produced. So the first mine produces more or less 220,000 tons of nickel annually. And that mine is Norilsk in Russia. and it's the lowest cost producer because it produces, you see on the y-axis how much what the cost is. Now, if metal prices go up, that is shown by this blue arrow, it means that all mines are making money, right? Because the cost is below the price to the market, and all mines are making money. In the scenario, in the previous chart, if you're in this dip, you're in the scenario of this below dotted line, some mines are losing money. Losing money leads to closures of mines, leads to consolidation of mines. Now, it seems that in the future, prices will go up. They're already up 40% compared to the last couple of years, but they will keep on rising. It means that all mines are making money. And it's no surprise that the mines on the right-hand side have the highest energy consumption, the highest environmental footprint. It's because they're the highest cost. So it's not only money, but it's also environment. So higher prices leads to higher impact on the environment, higher impact on the planet. So you see this little symbol of GSR on the left-hand side of the chart, on the right-hand side of Norilsk. That is according to our assessment of the economics of seabed mining, where we would enter the cost curve. If seabed mining would occur, it would go right into the cost curve around that spot. So you are very cost competitive, and if it's scalable, then basically two things can happen. Or the demand stays the same and the ones on the right-hand side have to close, or demand grows and then obviously everything moves to the right-hand side. So that is what is the opportunity of polymetallic nodules. So people often ask, is it economic? We believe so, because here you can see left-hand, and other people ask, what is the environmental footprint? What I haven't mentioned yet is that we have these 4 metals in a nodule. On land, you don't find those 4 metals together. You don't find manganese and nickel and cobalt together. So it actually means you need minimum 2, sometimes 3 land-based mines to recover the same amount of metals. That again translates in economic aspects, but also in environmental aspects. So finally, I will conclude with our schedule. And I've highlighted a few points already. So we started this adventure in 2010. We got a license in the period 2012-2013. Then we did a desktop study in 13 and 14, which led to us saying, okay, there's no red flags from a technology perspective. This can be done. It needs engineering, but this can be done. And that led to pre-feasibility from 2015 to 2021, where we built Patania 1, built Patania 2, worked with partners on a flow sheet on how to extract the metals so we could close the business case. That brings us to the feasibility stage from 2022 to 2024. And now a lot of the things need to come together, because we need, on the one hand, more engineering for Patania 3, so we can do what's called a system integration test. It's a full-scale test where everything subsea is full scale. There is no way to, there is one exception to downscale a system integration test, and that is only feasible if your nodules are small. Our nodules, the average size is more or less 7 to 8 centimeters. So these are relatively big chunks. That determines really, if you want to do a system integration test, that determines the size of your nodule, determines the width of your pipe that you need to use to suck the nodules to the surface. Because we say in the dredging industry that your riser needs to be at least 3 times the diameter of your product. So 3 times the diameter of a nodule needs to be the width. Otherwise, you get clogging into the riser. We need to put clogging. So that determines the size of your riser. So that determines the size of a pilot mining test, an integration test, because I cannot use a smaller riser. So it's commercial. Everything below is commercial size. There's one exception again. The metals company, they have tested a system just last month, in the last couple of months. The nodules found to the east of the Clary-Clipperton zone are known to be smaller. If you have smaller nodules in the size of, let's say, golf balls, then again, with that same philosophy, your riser can be much smaller. If the diameter of the riser, if the diameter is smaller, there is options to use, for example, airlift, which the metals company has done, airlift to bring the nodules to the surface. And that is the test that has been done. We are looking at centrifugal pumps with a larger diameter riser. Everything subsea commercial, and that test is foreseen for 2025. So while that engineering needs to happen, the systems need to be built. we're doing this at the same time when the regulations need to come together, because the regulations provide certainty for investment. If those regulations are not delivered, then we will not move to system integration test. And once the system integration test is delivered, we go to a permitting phase, which will take at least a year. And once the permit is delivered, we go to a construction phase. So it looks at production earliest by 2028, say 2029. So this is the more or less 15, 16 year schedule that we are on. We're a bit over half, still have a long way to go. But I think the last 10 years was aspects that we could control. This is engineering, it's money, time, it's engineering aspects. The next 5 years will be more about social acceptance, regulatory acceptance, etc. These are not things we can control. It's our job to develop the science and to bring the science. But in the end, if we don't want to listen to the right science, then it's very difficult to develop these types of new industries. So that would be my last question. So I leave it for the floor. If you have questions, I'm happy to answer. Thank you.
Yes. Thank you so much. Is now our chairman. We don't have now, Professor Eduardo, so much time for discussion. Let's try to stick 20 minutes. Okay, and then your final remarks. Okay, sorry for because the room is scheduled for another activity. I ask for your understanding because it was important.
What is the limit?
20 minutes, 25 minutes. Okay, I'm counting.
Okay, let's go quickly. First of all, I want to ask people in the room if they have some questions for our speakers or do some comments, because the floor is also possible for you.
And online, Professor.
I'm online.
You can raise your hand.
If these people write in the chat, and Paula or you can repeat the question, is better. Please go ahead.
Yeah, I have two questions for Chris. Very nice presentation. The first thing I'm sure you are aware of, but I'm looking from a geological perspective, that you don't need necessarily to go to the ocean floor to study nodules. There are many areas where the ocean floors were lifted by the tectonics, and you can study these nodules on land. There's one area also in Slovenia, an interesting story. The first ferromanganese alloy was made in Slovenia in the end of the 19th century, because they were putting these nodules in the smelter, and they made the first ferromanganese alloy. So, but the second really question is, you say that the size of the nodule determines the size of the riser, but why don't installing the crusher on the nodule collector?
Yeah, that is a good question, and something that we studied around 2015 and 16 as well. So back in the 70s and 80s, they did tests back in the 70s, 80s, and they also installed a crusher. At least Lockheed Martin installed a crusher on their device. And after, I can't exactly say how long, but it must have been like 15 minutes, the crusher got clogged. And you would think, okay, how would a crusher get clogged? So a lot of tests were done on the behavior of the nodule on the surface, but nobody did it on the sea floor. If you take a nodule onto the surface and you crush it, it breaks into tiny pieces. But if you crush a nodule at 4,500 meters, it behaves like a gummy ball.
Plastic.
Plastic, really. So in order to know that, in 2000, I believe, 17 or 18, JPI Oceans was going on a mission to the Clarion-Clipperton zone, and we suggested to install a pressure bank. We built it and we delivered it to JPI Oceans, and they put it on their ROV, and it was a pressure bank just to look at the pressure it would have to crush a nodule and to see how it would behave. So we did that back then, and we then said, okay, we're not going to use crushers on the seafloor.
Okay, thank you. Interesting. Didn't know that.
No.
Because the pressure coming from all directions. In the land, you crash in one direction, and the other direction don't have pressures. Don't protect.
Okay. So new type of crusher is invented.
Okay. More questions?
Maybe for supplement for Chris, what is the energy consumption in the different parts, in the collector, in the riser, in top, in the processing? Do you have an idea of the per ton or in percentage? What are the distribution of energy consumption?
Energy consumption compared with the collecting and the lifting. The lifting consumes much more energy. I remember more than 3 times than the collector.
2/3?
3 times,
3 times.
or even higher. Yeah.
Okay. 1/4 for collect, 3/4 for rising.
And then in that surface, the processing, separation, compacting, water, filtering.
You
Only just for lifting up.
And for all the
It's
other,
different.
so it will be
Yeah.
some rough numbers.
I didn't calculate it full scale procedure. What kind of separation principle is applied? For instance, this cyclone type is much more energy. And in my opinion, this natural, the gravity energy should be used to reduce the energy itself. From
ship, gravity
from
separation
on
in ship.
on the ship forward.
And Chris, do you have numbers?
I don't know the details. I know we intend to use 40 megawatts on the vessel in total. I believe that the vehicle is 1.5 megawatts, but I don't know exactly the different components between the vehicle and
1 to 10.
1 to 20. The figures is 1 to 20.
Yeah.
Transportation is 38.
No, you have a ship as well, huh?
Ship. Okay, rising, but ship is also count.
The ship is.
I know what they need understand.
Okay.
I know what they need understand, and the energy of ship is also count.
Yeah.
I was wondering if there's any need of consideration to leaving kind of untouched nodules on the ground, not like pillars for the mine to keep the roof, but pillars like keep the life for easier rehabilitation. So when you have a mining path scenario, is it considered to give some certain stretches, or it doesn't need to do that because you are just mining certain patches, and because of the uneconomic ones will be perfectly fine for rehabilitation? What is the strategies?
Yeah, I think there we follow the last strategy, the fact that we leave enough behind in order to keep that ecosystem in place. But on top of that, there are rehabilitation programs currently being tested. So when we tested our vehicle last year, there is a scientist, Sabine Gollner from NIOS, that took artificial nodules and deployed them, and real nodules, and deployed them back into the impacted area by us. And they put like these different frames, with each frame 100 nodules back on the seafloor. And they're now revisiting it because today, actually, I haven't told you this, but 2 weeks ago, a vessel, JPI Ocean's vessel, left from LA back to the German and Belgian area to revisit the impact area 18 months later. And they're not only going to see, the blanketing, how far did the blanketing eventually reach, and has it retreated due to currents, for example, but they will also look at how is the biodiversity recovered. And they will also look at how is this new substrate that has been brought into an impacted area, is it attracting, for example, life, sessile fauna, whatsoever. So it's all being looked at. Obviously, this this is going to be a long-term study. These nodules are going to be there for the next 30 years, and every year, if we have an opportunity, we're going to see and see how the environment has reacted.
Thank you.
Ulrich has a question. I think
another question is, we need to be correct. So first, you commented on the metals company mining. They didn't do mining. There was no mining regulation, and that's why it was a testing of mining equipment, right? So we have to be correct with that, because otherwise it creates confusion. Same as people always talk about the German claim, the Belgian claim. There are no German claims, and there are no Belgian claims, and there are no Canadian claims. We do have contractors, right? And the contractors have sponsoring states, as Chris pointed out. And the sponsoring states, actually, their responsibility is to make sure that the contractors follow regulations, right? So it's not just ISA, the regulatory body, but also the sponsoring states, making sure that the contractors, sometimes the contractors are governmental agencies, like in the case of Germany, the German Geological Survey, but still they are controlled by their own ministries of environment, of economy, and so on, right? So there's a mandate of sponsoring states to make sure that it's not happening. That's important to have this, to keep this in mind. Also, with JPIO, the current cruise is not paid by or not organized by JPIO. There are JPIO scientists on the ship, but the funding comes from the German Research Foundation, and during the environmental program of GSR's activities, their own claim or contract area as well as BGR's contract area, then the ship was actually paid by the German contractor, not by JPIO. Just to be correct, right? So.
Yeah.
Thank you for the clarification. Ulrich. So Willem de Moor from JPI Oceans, by the way, and thank you very much for the presentation and for the clarification. Just a question on the sediment plume, because you touched upon that. There will obviously be a sediment plume due to the collector, probably also maybe a sediment plume in the riser, coming from the riser, and then discharge from the ship. Are there already some ideas on how to limit the impact of the latter two?
About the mid-water plume. Yeah. So first, again, everything starts with measuring. So in 2018, we worked together with MIT to make an artificial mid-water plume. So we used Sally Ride, which is a US research vessel. It left from San Diego, and it used sediments that we collected at the Clarion-Clipperton zone, sediments from the seafloor. And we basically, after first doing different types of sediment coming from land and trying to monitor it with the devices. Finally, when we had an idea on how to monitor it, we basically pumped the sediment from the Clarion-Clipperton overboard at 120 meters. And it created this plume. And basically, they had the AUV flying through it, and they developed a monitoring system. I don't know if you're aware of that test, but they published on it. A year later, I think, they published on it, and basically concluding that now they know how to measure. And they could also then extrapolate if a plume behaves this way, what if you do this 24/7 with this type of volume, etc., etc., etc. And that paper is available, it basically, don't know the numbers by heart, but they have a table in there that says if you have 20 mining operations, which is huge, we won't have 20 mining, but let's say you have 20 working, going all year round. It was like the volume of water impacted was like very small because, I don't know the number, we have to look it up, but because of the immediate suspension, clearing of this plume, the distribution of this plume into the water column. The water column is so huge, right? And then they could see that at like 600 meters from the exit, there you would reach the same in situ density as the surrounding water. So with that in mind, we now need to decide what is the best place to do that, either on the seafloor, bringing the sediment back into the mining area, or somewhere in the mid-water column where there is the least impact on the. Today, it hasn't been decided yet. Now, the only way to reduce that plume would be to leave as much of the sediment on the seafloor. We're now thinking it's like 95 on the seafloor and 5% into the rise. The more you can leave on the seafloor, obviously, the least you have to put back. But the good thing is we have now science. From the science, we need to know what the impact on the biology is. We have now this test of the metals company, and I believe they have brought the return water back to 1,200 meters or 1,500 meters. I'm not sure. But they had a monitoring team on it. MIT people were there, so I'm hoping that they will give some feedback on that experience as well.
Yeah, great. Thank you. Maybe can I just add on this? There will be a team on the hidden gem on the return vessel tomorrow by ISA. ISA people doing inspection, right? So all the activities by the metals or by NORI, actually, to be correct, NORI, will be inspected tomorrow and the day after, right? So all the data and so on. So nothing is happening in the dark, right? Despite the fact that people want to make us believe that it is. That's not the only inspection.
Don't forget my question I do before about the compatibility regulations for national jurisdiction to the reason.
Yes, that's right. So what we know now from Mauritius, from Norway, from Cook Islands, they all follow the process by ISA, right? So we are in close discussion with them, and they adopt as far as they can do just now the regulations based by ISA. So there's nothing. There's no side way, it seems, right? It was a little bit different with Papua New Guinea and the activities by Nautilus, but just now they follow closely the regulations which are put in place by ISA.
Okay, thank you. Thank you very much. More 1-2 minutes or?
5 minutes, okay?
5 minutes. Today I don't listen to nothing about the noise. About the pumps, the machines. I listen something. Okay, machine. The money machine. The noise is not a big problem. The boat is a more problematic. All the boats or ships in the water. But I don't understand if your buffer is in the middle of the pool of the water, of the buffer for the nodules is in the deep.
Very close to the collector. It's about 100 meters.
Above the collector.
Yes, above the
collector. But the noise and the temperature of the water when they return to the deep sea again, I understand it's important to return to the deep sea, but in the meanwhile the temperature rise or decrease, I don't know, but it's possible to these two issues is real a problem or is only in our minds.
This is actually also inspected, right? So we ask them to measure temperatures, volumes of returned water. I can't give you information now because it's just happening.
Yeah, so tomorrow, right? Of course, only to understand
inspection. Yes, that's right.
Because intelligent noise is a vector of the developments. Not only the mitigation, the cancellation of the noise, or even to understand the propagation of the noise of the equipment and so on.
And I forgot to say that the inspection protocol will be up on ISA's webpage, right? So also it's open to anybody who's interested in read what they did during the testing.
Okay, thank you. I go to close. Okay, first of all, I'm very happy today because today you have a smooth, it's not a discussion, but a smooth conversation about these topics. I am happy because we see different perspectives. Now we understand better this landscape. This landscape is very complicated. Regulations, people from technology, geology, biology. All people have own claims about this environment, industrial environment, and for me, it's more today. With my background, it's more clear some paths you need to do, and the pathway to success is clear it's not totally clear. Sorry, it's more clear for me. And I also understand you need to work more tight. It's fundamental to work more tight together, all people together, because we need to learn a lot of things. You see, it's amazing when I see your presentations again. I visited you 2 years ago, not 3 years ago, I suppose, and I am astonished with your technological developments in the past 209. We wake up for that only 211, and you are developed before a lot of things, and we need to all people need to learn with each other to have shortcuts. Because if I don't learn with you, I go to the same errors you have done, and I need to learn with you. I need to learn with Is. I need to explain very well regulations. Sometimes you don't see the impact of our actions, and you need to understand also. I need to understand real industrial experience, because you put things in the hands-on in the real place. Normally we work in the lab with beautiful things, okay, not with the dirty. We have good experience in the land, in the open pit mines give us insights for the risky and the dirty environments. But the real environment we need to learn, and we need to participate more together. The number of players is if you go around the table, the number of players is in two hands. I see a lot. Nautilus, I listen to Nautilus, Nori, DEM, GPI Oceans, ISA. But it contribute
only on the scientific side.
Scientific side, okay.
Yeah.
And the number of players is so small. We need to be. We need to all work together. And our side, from our side, we will continue to try to in this area and bring more people if you want to work with us or work together. And I hope next year we are here with different players again. Try to bring newcomers. And I said in the beginning, I hope in the few years that the fact is in blue and not in black. But today we start to open. In 5 years we start to open the curtains. But today I see a small window start to appear. And thanks to you, thanks to Chris, thanks to SUP. For us in ENESC, it's very important to learn today with your experience. And sorry, no, I forget Our Lady. To mention Our Lady also. And we learn a lot. I learn a lot. I don't know if you other participants learn, but I hope. And thank you very much for your efforts. And I hope to see you in some of you in January in the kickoff meeting of the Trident. Okay, maybe Thomas coming, because Thomas sent me an email and now asked me if it is possible also to participate in the advisory board.
Yeah.
Thomas write a paper. You mentioned in science from MIT. Maybe we join in January. I don't know if you have an open session in January. If it is possible to have an open session, 1 or 2 hours for other people are not belongs to the project and don't belong to the advisory board. We will see and we will communicate to the other people. Okay, thank you very much and safe return. The people now could go to jump to next mean demonstrations. Luck for the people. And I hope everything runs very well. The people go to home. Have a safe return.
So you will have the final word in just a few seconds, because you are our chairman, but just a few acknowledgements very quickly. Paula and I would like to thank to all our sponsors, Tech4C, ENESC Tech, EIT Raw Materials and Insight Upscaling Project. Our sincere acknowledgements to ENESC Brussels Hub. Thank you for having us here and the way you treated us in your home. You were an awesome hosting, Ricardo Miguel. Thank you so much. A special thanks and our tribute to our former chairman. He was part of this story of In the Black, and he will always be. So our tribute to the one and only Dr. Stef Kapuzniak, a huge hug from all of us. This was a great way to celebrate 5 years of In the Black, with amazing speakers and a lot of interesting discussions. Thank you for the remarkable presentations, your valuable work, and we are looking forward to this new era of ocean exploration. And I think that we still have a lot to discuss. Thank you to all the participants in person. Thank you so much. Thank you for coming. Thank you to the attendants online. Also, we cannot forget all the speakers involved in the previous editions of In the Black. You were all responsible for raising the high standards of our event. Thank you so much. And last but not least, to Professor Eduardo Silva, the mentor. You were the inspiration every year to motivate In the Black community and to almost and to almost become a cult. So In the Black is now a cult. So In the Black is now a religion, and we are all being converted by him. So thank you for bringing out the best in us, Professor Eduardo. We would follow you to the Mariana Trench and even to the moon. So from deep sea to outer space. You are all invited also tomorrow to the final conference of UNEXUP project in Nemo 33, the aquarium. So thank you so much and see you next year. Professor Eduardo, the last word.
Thank you very much for your kind words, but my words is your words for all people. And in a few months, we meet again. Bye-bye.
Bye-bye.